Hello everyone, welcome back. We're now going to put into practice these kinematic formulas that we derived in the last video. So we're going to be working with both constant motion questions and accelerated motion questions. Before we start solving these, we have to abide by a couple of important rules here. First of all, before you do any of these questions, you have to determine whether or not we have constant motion or if we have accelerated motion. And the reason being is that the formulas are not compatible with each other. Constant motion formulas only for constant motion, accelerated motion formulas only for accelerated motion. Now, technically speaking, you can use the accelerated motion equations for constant motion, simply set the acceleration to be 0 and your v1 and v2 would be the same number, but you can't go the other way around. So here are the big ideas. With constant motion, we have the following kinematic parameters: d, v, and t. Now, reminder, that's technically delta d and that's technically delta t. We just dropped the deltas to make the notation a little bit easier to work with. So to solve any problem, you need to have 2 out of 3 of these parameters known. So long as you know 2 of the 3, you can solve for the third unknown. That means if you have v and t, you can solve for d. If you have d and t, you can solve for v. And if you have d and v, you can solve for t. And for constant motion, we only have one formula, and that is v is equal to delta d over delta t, or the variance d is equal to vt, which is really delta d is equal to v delta t, and t is equal to d over v. Technically, delta t is equal to delta d over v, so on and so forth. Let you in on a little secret. That's the usual form that we work with. And the main reason why, no fractions. Now with accelerated motion, we've got 5 kinematic parameters. And those are your distance/displacement, or d, your initial velocity, your final velocity, or initial speed, final speed, your acceleration, and the time. Now with these, you need only 3 out of the 5. And the reason is that each one of our formulas only use 4 at a time. So let's say, for example, this. Let's say we were given the value for d, we were given v1, we were given v2, and you're asked to find acceleration. So what you're going to do is you're going to look for the one formula that doesn't have t in it. And that one is our equation number 5, which is v2 squared is equal to v1 squared plus 2ad. And in this case, if you were to isolate for acceleration, we would have to do Bedmas in reverse, which I like to refer to as SAMDEB. So you have to do your subtraction addition, followed by multiplication division, then exponents, then brackets. So since we have the plus sign here, we move this over through subtraction. And then if we want to get a by itself, that means we got to move the 2 and the d, and those are attached through multiplication, and the opposite of multiplication, of course, is division. All right, so that's just a little preview. Now what we're going to do is actually solve some practical problems. So we have to first determine if it's constant motion or accelerated motion, and then what we're going to do is we're going to take an inventory of the given information. So let's jump right into it. So our first question: a car drives at a constant speed. All right, well, question. This is a tough one. Is it an accelerated motion question or a constant motion question? Well, I'm assuming by the fact that it says constant speed, we know that it's going to be constant motion, which means one formula only. So we have a car that drives at a constant speed of 108 kilometers per hour. So what that means is our v is equal to 108 kilometers per hour. Okay, so now, next thing what we do is we want to look for any other given information. So then we go to part A and see if there's anything written there that there are any new numbers. So part A, what is the speed in meters per second? No new numbers. In part B though, we have been given this. How far does it travel in 60 seconds? Well, 60 seconds is a measurement of time. So t is equal to 60 seconds. One note, I also think it's best practices to put the subsection that it's from in the question. So part A, because this number, 60 seconds, may not apply to any other part of the question. And a prime example is this. How long would it take to drive 3 kilometers? All right, so the next question is, what does kilometers fall under the category of? Speed, time, or distance? And the answer is obviously distance. So the question is presented in such a way that we're expecting that the answer should be with 3 sig figs. Okay, so now the next step required to find. So in part A, we want to figure out what the speed is in meters per second. So what we're going to do is we're converting from kilometers per hour to meters per second. Part B, how far does it travel? It's asking for the distance. Funny thing to note, sometimes we conflate how far with how long. For example, and this seems to be in sort of typical of at least Southern Ontario, but I think this might be a North America-wide phenomena. But generally speaking, if someone asks you, how far is such a place? Typically, we will answer with a time. So for example, how far is it to Toronto from London, Ontario, for you internet people that aren't from Canada. But how far from London, Ontario to Toronto, Ontario? And generally speaking, we'll say, it's about 2 hours. All right, well, 2 hours is not a measurement of distance. It's a measurement of time. So we often get the two conflated. So when the question asks how far, it's specifically asking for the distance. Part C, how long would it take to drive the 3 kilometers? So we're looking for time. So the formula, D is equal to VT, or V is equal to delta D over delta T. Now, the reason why I write it like this often is because I do want to remind people that it is delta, but if you just wrote this, that's fine. Just got to remember that's actually delta. All right, so the first thing, we're going to convert. So for part A, we're going to convert 108 kilometers per hour to meters per second. Now, we did this back in the measurement and analysis unit. So as a quick reminder, set up your unit as a fraction. And then what we're going to do is we are going to eliminate the numerator and denominator one at a time. So it doesn't matter. You can start with the kilometers or you could start with the hours. It doesn't really matter. So I'm going to start with the kilometers. So since the kilometers on the numerator, I have to make sure that it's on the denominator in my fraction here. I know the conversion from meters to kilometers is 1,000 to 1. And of course, now we can cancel out the kilometers. Next, it's the hours. We have to get rid of the hours. Well, if I have hours on the denominator, it must appear in the numerator in my fraction over here. Okay, so now, here's the thing. Most of you know that there are the conversion from hours to minutes, then minutes to seconds. But we do this conversion so often that we're just going to, from now on, go directly from hours to seconds. And since there's 60 minutes in an hour and then 60 seconds in a minute, you actually multiply the two. And as it turns out, is that 1 hour equals 60 times 60 or 3,600 seconds. Okay, so now the hours cancel out. So we're left with 108 times 1,000 divided by 3,600, and the units will be meters per second. And that works out to 30 meters per second. But there's a problem. And this would actually not be an acceptable solution. And here's the reason why. 108 has 3 sig figs. The way I have it written here, the 30 meters per second, it only looks like there's 1 sig fig. So it must be 30.0 meters per second. So that's it. That's the simple conversion. However, it turns out that this can be done much more easily. We actually have a shortcut. So I'm going to show you the shortcut. So the shortcut for converting kilometers per hour to meters per second and vice versa. And here's how it works. Kilometers per hour, meters per second. So when you want to go from kilometers per hour to meters per second, you divide by 3.6. Now to go from meters per second to kilometers per hour, you just multiply by 3.6. Simple as that. However, there's an important note. This conversion only works for specifically kilometers per hour and meters per second conversions and nothing else. So if you have a unit that is other than this, this will not work. So for example, accelerations in meters per second squared, this does not work. You have to do it using this method over here. So again, only for kilometers per hour to meters per second, or the other way around, meters per second to kilometers per hour. And again, we do this a lot. So the 3.6, that's what you do. So you divide by 3.6 to go from kilometers per hour to meters per second, or the other way around, you multiply. And if you have a hard time remembering which one is divide and which one is multiply, the easy way to look at it and think of it is that the unit for kilometers and hours are bigger than meters and seconds. So it makes sense by dividing, you make it into something smaller. I mean, it's just a way of remembering it. I mean, it's just coincidence that it kind of worked out that way. But anyway, that's just a thought. Okay, so now let's move on to the next part. And also let's reduce some of that real estate there. Okay, so now part B. So in part B, we're asked to find how far it travels in 60 seconds. So what we're going to do here is we know that we're looking for the distance. So what I'm going to do is I'm going to take an inventory. V and T. All right, so let's take a look at what we got. Distance is what we're looking for. Now we know our speed, and we know it two ways: 108 kilometers per hour or 30 meters per second. And the time, 60 seconds. So the form of the equation I'm going to use is D is equal to VT. And which speed do we use? Well, that's based on the fact that the time is in seconds. So we need to use the speed that also has time, the time portion of the unit in seconds. So it's going to be this 30 meters per second and 60 seconds. You can't use the kilometers per hour. So that works out to 1,800 meters. Therefore, the distance is equal to 1,800 meters and 3 sig figs. So we have to have the tilde there, which is equal to 1.80 kilometers, dividing by 1,000. And we don't need a tilde because of the weird rule. Now moving on to part C. So with part C, we're asked to figure out the time, and we have the speed, and we also have the distance. And I realized I made a mistake. That's part B, and that's part C. Oops. Well, we fixed it now. It's cool. It's totally cool. Okay, so now we're finding the time. So again, time to take inventory. So the distance is 3 kilometers. The speed is 108 kilometers per hour, or 30 meters per second. And the time is unknown. Okay, so now here's the thing. The distance is in kilometers, so that means that we need to use the speed that is in kilometers per hour, which is unfortunate because that is going to make a kind of a terrible answer. A lot of decimal places with this one. So we're going to solve it, and the version of the formula that we're going to use is T is equal to D over V. Now again, you don't have to memorize all these. If you have one of them, you can get the others. Now here's the thing. There's another. Some people use what's called a formula triangle. I'm not a huge fan of the formula triangle, but it kind of works like this. So if you're looking for V, that's going to be D times T. If you're looking for D, that's going to be V divided by T. Wait, what? No. Oh my goodness. All right. I mean, I was just testing you. I was just trying to see if you were paying attention. Yeah. See, this is why I hate formula triangles. They make me look stupid. Anyway, try that again. Rats. If you're looking for D, thank you for glitching out again. Okay, if you're looking for D, that's going to be V times T. So D is equal to V times T. If you're looking for V, that's going to be D divided by T. And if you're looking for T, that's D over V, and that's what we got right there. Anyway, you can use that, but it's stupid. I mean, if it helps you, awesome, but I think you should be able to just do simple algebra. But anyway, I digress. Okay, so now substituting in, here we go. So we have 3 over 108, which actually works out to 1 over 36, or 0.02777. Just, it repeats. So we have to round that off to 3 sig figs. Also, we have to put in the proper units, and the proper units are hours in this case. So that's going to work out to 0.0278 hours, the appropriate number of sig figs. All right, well, that's really gross, but here's the thing about that. There's actually another way that we could do this. The thing about distance, that 3 kilometers is also equal to 3,000 meters. And then that way we can use the V is equal to 30 meters per second. So when you do it this way, that works out to 3,000 over 30, and that works out to 100 seconds to 3 sig figs. You know, that's a lot nicer. And again, just to prove it to you, if you take 100 seconds and you divide by 3,600, you get that. All right, simple as that. So again, that question, all constant motion. Next, question 2. All right, question number 2. If the car in question 1 has to stop suddenly. Okay, so now here's the thing. It's referring to the first question, which means we need to borrow some information from the first question. Secondly, we have to determine what type of motion this is going to be. So is this going to be constant motion or accelerated motion? And that ought to be your clue. So it's accelerated motion, which means we can't use this formula. Nope. So now we have to use those 6, I guess, but really it's about 5 kinematic formulas for acceleration. And again, as a reminder, with accelerated motion, we have d, v1, v2, acceleration, and time. Those are the kinematic parameters that we need to work with. And to solve any question, you need 3 out of the 5. All right, so first of all, we're going to borrow that information. So we know we're talking about the car in question 1, and that car was traveling at 30 meters per second. And then the car suddenly comes to a stop. So for part A, our V1 is equal to 30.0 meters per second, and our V2 is 0 meters per second. The other information, we know that it stops in 6 seconds. So our time is 6 seconds. And in part A, we're asked to find the acceleration. So part A, acceleration. Okay, so now in part B, we're asked to find the car's stopping distance, which really is just distance. So now that information that we have here for part A also applies to part B. So for part B, we're looking for distance, and that means this is for A and B. Now, part C, we're asked to find the stopping distance again, but this time if the car was moving 10% faster. All right, so a lot has changed here. So in part C, we're looking for the distance again, but the issue is this. What that means is the V1 is not 30 meters per second anymore. So in part C, the V1 is going to be 30 meters per second plus 10%. Now, when you add 10%, you're adding 10% of 30. 10% of 30 is 3. So it's going to be 33 meters per second. And the other way to look at it is when you add 10%, you start with 100% plus 10%. Well, that's equal to 110%, yeah? Which is, as a decimal, 1.1. So take 30 times 1.1 and you get 33 meters per second. That's the other way to think of it. Or 10% of 30. And remember, of is just another way of saying multiply, and that's 0.1. And so that equals to 3 meters per second. Then you add the 30 and anyway, you got it. 33.0 meters per second. So now we got to figure out some other stuff. So we know that the V1 is 30 meters per second, but it did say the car's stopping. So that does mean that our V2 is equal to 0 meters per second. Okay, so now with question C, we have an issue. So I'm just going to, I usually discuss this a little bit later, but since we're here in this spot, let's talk about it. Okay, so first of all, for part C, we're looking for the distance, question mark D. All right. Next, we have V1 and V2. Now, we need one more kinematic parameter in order to be able to solve for the distance, because we only have 2 of the 5. We need 3 out of the 5. And invariably, someone at home is saying, but we know time! Exclamation point, exclamation point, exclamation point. Like, what gives? I'll tell you what, no, you don't have time. You see that 6 seconds? That 6 seconds was associated when the car was moving at 30 meters per second. But now we're moving faster. And since we're moving faster, it's going to take more time to slow down and come to a stop. That means it's going to exceed 6 seconds. assuming that we are in a maximum braking situation. So in part A, we're stopping as quickly as the force of friction will allow us to stop. And we can do that in 6 seconds. But if you're going faster, it's going to take longer. So the time is invalid. So that means we need acceleration, but we don't have it. But we are finding it in part A. So the one thing we have to take into consideration is that it turns out that the rate of acceleration, and you don't know this yet, and we will talk more about this when we get into the unit where we discuss friction specifically. But the big idea is this, is that the force of friction that stops a car is independent actually of how fast you're going. And it is only related to the road conditions and the type of tires you have and the condition of the tires. Now, this isn't an ideal situation. Of course, in a real world situation, there are other factors. So for example, when you hit on the brakes and you start skidding and then the tires get hot, if they start to melt, then the force of friction is different, yada, yada, yada. These are more complex problems that you won't even address at the high school level. Those are more university level questions when the acceleration varies. So for our purposes, we're going to work in what I refer to as physics la-la land, where things like the force of friction are completely consistent and the rate of acceleration is completely consistent. Now, in a real world situation, that is not entirely accurate, but we're just learning, we're new. Okay, so let's jump right in. So for part A, we're trying to find the acceleration. So again, I'm going to take my little list here and write down everything that I know. All right, so in green, I'm writing V1 is equal to 30 meters per second. And the reason why that is a given. And we know that with a very, very high degree of certainty. We know that the final speed is 0 meters per second. And that is also with a very high degree of accuracy because again, it was given. It's precisely known. And then the time of 6 seconds, that is also precisely known. We are looking for the acceleration, which means we're going to pick the formula that does not have distance in it. So let's refer to our list of equations over here. So these are the accelerated motion equations, and these are equations 2 through 7. Now, remember, 6 and 7 are basically the same equation. All right, so process of elimination. We want an equation that does not have distance in it. So these equations here are all disqualified because they have the letter D. That leaves equation 6 and equation 7. So which version of the equation do we wish to work with? I'm going to recommend this one. And the reason why? Because the acceleration is already isolated. So A is equal to delta V over delta T. Now this is ludicrously important. You have to remember what the delta means, and that is V2 minus V1 over delta T. So basically, here is my rule. While you're new, you're going to show me all of these steps here. Now, you always start off with this. You always start off with the equation, and then you manipulate the equation to isolate for the variable that you want. But I don't always make people write this step, especially in grade 12, but grade 11s, I make grade 11s do this. Why? Because this tendency. Students will write this and forgetting that the delta is in front of the V and the delta is in front of the T, and then they'll put one or the other velocity, but not both. So no. All right, so next, substituting the numbers in. I'm not going to carry all the sig figs in the calculations. We'll just make sure that we have them at the end. Now, this is also another thing too. By doing it this way, writing V2 minus V1, you get the order correct because it's 0 minus 30, not 30 minus 0 over 6. And that works out to negative 5.00 meters per second squared. Now, technically, that didn't give us, we weren't given a direction, but this is technically a vector. So that would be 5 meters per second squared backwards, which makes sense because if you're moving forward, the thing that's stopping you is pushing you in the opposite direction of your motion. So therefore, the acceleration is equal to 5 meters per second squared backwards. Now moving on to part B. So in part B, we're looking for the stopping distance. So we're trying to find D. And again, we bring in our list and we're going to fill it out with what we know. So D is unknown. Our V1 is known, and that's 30 meters per second. Our V2 is 0 meters per second. Our acceleration is -5 meters per second squared, and our time is 6 seconds. Okay, why did I do that? There's a reason. Our value for A, we found it. We calculated it in part A, which means that it's subject to potential error, whether it is rounding error or actual computational error. For example, us simply making a mistake. The rule is that you try to avoid, if you can, using calculated values, and you try to rely on the given values as much as possible. So in this question, we have 3 green givens and 1 amber given. We're going to work with the 3 green givens because those will give us the most precise answer for our distance/displacement. Okay, so that means what we're going to do is we're going to avoid the equation any equation that has acceleration in it. So, process of elimination. Nope, 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 and no. So, as you can see, there's only one, and that's this equation right here. D is equal to 1/2 V1 plus V2 times T. Okay, so it's already in the form where D is isolated, so we can just substitute our values in. And we get 90 meters, and specifically positive 90 meters, because we're moving forward. So therefore, our displacement is 90 meters forward. All right, so now for part C, we are again asked to find the distance, but this time, this question was asking for the stopping distance when we were going 10% faster. So our V1 is 33 meters per second in the positive. Our V2 is 0 meters per second because we come to a stop. And we know that our acceleration is -5 meters per second squared. And I have to reiterate, we don't know what the time is. That 6 seconds is not valid in this case. That only applies for when we were going at 30 meters per second. So now we have no choice. We have to use this accelerated value. So in terms of assessment, here's how I generally go about doing things. If you have a choice to avoid using a calculated result, I expect you to do that. But if you do use one of the calculated results and you got no error, you made no mistake, what I will do is I'll just give you a warning of basically explaining that's a dangerous practice, or potentially, hardly dangerous, but you know where I'm getting at. And simply as a warning, suggesting that is, a risky approach for the aforementioned reasons about, calculator and rounding error. However, if you do use this calculated result and the calculated result is incorrect as a result of an error, you're going to end up losing double the amount of marks. And the reason why is because you had a better choice. You could have chosen to use the given values only and not run into this problem. So it's kind of like, you're gambling a little bit. Sure, maybe using the calculated result will be a little easier computationally, but it does run a risk. So just remember that. The other issue, what if this situation happens here where we miscalculated the acceleration in part A, but we need it for part C? My policy is generally this, is if all the algebra is correct, but your answer is off because of a previously incorrect calculation, I will give you the marks for that part of the question based on your algebra. But the trick is you have to do it entirely algebraically. If you substitute your numbers in earlier on, forget it, because then you lose most of the marks, because then it's all nonsense. That's why we do things algebraically. It's much easier to see what the letters are doing than what the incorrect numbers are. But I digress. So let's move on and figure out which formula. So we have to find the one formula that doesn't have time in it. Okay, so disqualified, disqualified, disqualified. Oh, there's one. V2 squared is equal to V1 squared plus 2AD. So V2 squared is equal to V1 squared plus 2AD. Now, you are going to isolate for distance first. You are not going to substitute in yet. Isolate algebraically, which means that we have to do the SAM-DEB thing. So again, as a reminder, subtraction and addition first, which means the V1 2 squared has to go because of the plus sign right here. So V2 squared minus V1 squared is equal to 2AD. So now we're done with addition and subtraction, and now on to multiplication and division. And we have to remove the 2A, and the 2 and the A are attached through multiplication. The opposite of multiplication, of course, is division. So we get V2 squared minus V1 squared over 2A equals D. So D is equal to V2 squared minus V1 squared over 2A. Now, before we calculate, we're going to do a prediction here. Now, we know that the speed increased by 10%. So the question is, what percentage should the distance increase? Most people say 10%, which is a reasonable answer. If the speed increases by 10%, it stands to reason that the stopping distance might also increase by 10%. So since our stopping distance was 90, 10% of 90 is 9. So we might expect that in this scenario, it'll take 99 meters to stop. All right, well, let's see if that works out. Substituting in, that's going to be 0 squared minus bracket positive 33 squared over 2 times negative 5. Okay, listen up, folks. This is really important. This square only applies to the bracket and not the negative sign here. That is a common mistake. So what that means is the numerator is definitely going to be negative. But that's okay because the denominator is also negative, which means our distance is going to be a positive value, which is what we expect. So when we do this calculation, this actually works out to 108.9 meters, not the 99 meters that we predicted. So that may be a bit unexpected, but there's a solid reason for this. It has to do with the fact that in this equation, the velocities are squared. So as it turns out, the relationship between D and initial V is not a linear one, but a quadratic. Here, let me show you. So our equation actually worked out to be this, because the V2 was 0. So we got negative V1 squared over 2A. All right. But here's the thing. So I'm going to bring that negative out front, negative 1 over 2A, and that's V1 squared. Now, this whole thing here actually, because the acceleration is also negative, this whole fraction actually turns out to be positive. So what this means is that we can actually look at this equation as a proportionality. So I'm going to get rid of the equals, and I'm going to get rid of this negative 1 over 2A, because that basically behaves like a constant. So what that means is that our D is proportional to our V1 squared. So now, how that works is this. So if our V1 was 10% more, that meant that our V1 was 110%. So we can represent that as 1.1, because it's 1.1 times whatever. That'll give us our speed increase. So that's 110%. Actually, let's do this. So 110%, which is equal to 1.1. Okay, so now the D is proportional to that V1 squared, which is equal to, take that 1.1 and square it. That gives you 1.21, or 121%, or 21% more. So let's see if we see this 21% more. So let's take our example. In our example, the new stopping distance was 108.9 and the original was 90. Well, if you take 108.9 and divide by 90, you get 1.21, which works out to 121%, or 21% more. So if you express your speed change as a percentage / decimal, you can figure out what effect that's going to have on the stopping distance. So let's do a little list here. So we have V1, and then we have D, and we know that D is proportional to V1 squared. So what we're going to do is we're going to compare. So we're basically answering the last part of the question here. What effect what does this mean about speeding? Okay, so let's say we're on the 401. And on the 401, the speed limit is 100 kilometers per hour. So most people drive at 120. So at 120, that's a 20% increase. So what happens if we have a 20% increase? Well, that looks like this. That would be 120%, which is equal to 1.2. So now, to figure out what effect that would have on our D, we take that 1.2 and we square it, which is 1.44, which is equal to 144% or 44% more. And that's a sobering number. A 20% increase in your speed translates to a 44% increase in your stopping distance. So now let's talk about doing 130. So we're doing 130 kilometers an hour. Well, now that's a 30% increase, or 130%, which is equal to 1.3. Take that 1.3 and we square it. That gives us 1.69, which is equal to 169% or 69% more. So a 30% increase in your speed now translates to almost 70% increase in your stopping distance. And it gets worse the faster you go. So doing 140, we get 1.4, we square that, that's 1.96% or 196% or 96% more. That's basically doubling the stopping distance, the required stopping distance, with only a 40% increase in your speed. It is no wonder why car accidents at high rates of speed are so dangerous, simply because the average person does not understand physics. And as a result, the 400 series highways are littered with fatal car accidents every day. And so many of them are preventable if people just wouldn't drive like lunatics. Now, there's an interesting counterpoint to this. In Europe, the speed limit is 130 on most highways, save for a few countries. The Netherlands, I think they limit to 110 kilometers per hour, maybe 120. But many countries like Italy, France, Germany, their speed limits are much higher. So in Italy and France, for sure, it's 130. And in Germany, on the Autobahn, it's unlimited. Not exactly. There are regions where it's unlimited. But near the urban areas, they then reduce it down, mostly as a result of traffic volume. One of the biggest issues in terms of car accidents actually has to do with speed differentials. So it's not just people that are going fast that are the problem. It's the people who are going slowly in the faster lanes. So very terrible lane discipline coupled with inexperienced, reckless driving is the reason why in North America, we seem to have a much higher rate of traffic accidents than they do in Europe. That being said, however, even though there are fewer accidents in Europe because of the better driver discipline, the accidents that they do have tend to be more deadly. And it's just a matter of physics. If you're just ripping down the highway at 200 kilometers per hour in your tricked out Audi and you lose control, the chances of the accident being fatal are dramatically higher. And for the record, 200 kilometers per hour would be a 400% increase in the stopping distance. But I digress. All right, question 3 is up next. All right, sample problem number 3. And incidentally, Tom was a real person and one of my former students. He literally threatened to drop water balloons on my head on a daily, so I decided to make a question to honor his genius. In any case, Tom is a comedy genius. Not relevant to the question, but it's true. Being such, he wanted to play a joke on Mr. LaRusso. He noticed that Mr. LaRusso walks below a window every day. With a water balloon in hand, Tom estimates Mr. LaRusso's walking speed to be about 2.5 meters per second. If the window is 10 meters above the ground, how far in advance should Tom drop the water balloon, assuming Mr. LaRusso is 1.800 meters tall? All right, so a couple of things that are going on here. 1, we have a water balloon that is falling. 2, we have me who's walking along the ground. So in this problem, we actually have things happening in the y-axis and things happening in the x-axis. Specifically, my walking part is happening along the x-axis, and that is constant motion, where the water balloon is being dropped and it's subject to the acceleration due to gravity, which I did mention as a little aside in a previous video, that is 9.8 meters per second squared down. So before we start getting into the givens, it's probably a good idea just to talk about the physics of what's going on. All right, so we'll start with the ground here and an exceptionally high quality illustration of me. All right, so here's the deal. The top of my head is 1.8 meters off the ground. Now this water balloon is being dropped over here. So the big idea is this. I'm walking in this direction along the x-axis at a constant speed. So basically, I'm going to be trekking along here at a constant speed. And then we want it so that the timing is that the water balloon hits me in the head when I am right here. So basically, this balloon up here has to fall down at the exact same time that I am here. So there's the sort of lighter version of me. So as I trek along from this point over here to right underneath where the balloon is, this balloon is going to have to make the traverse down and hit me right smack on the head. So this right here, this represents my distance / displacement in the x-axis. So I'm going to call this d subscript x because this indicates the x-axis. And this is actually what we're trying to find in the question. That's the how far in advance from this point here, the target point. So let's talk about what I'm doing. I'm walking at a constant rate, and that rate is given. So what we know is we know what my Vx is. Now, it's constant motion, so it's just a V, but the X indicates that it's happening on the X-axis, and that is 2.50 meters per second. Now, the Y-axis, well, that's a little bit different. Now, this water balloon is falling, and it is falling this far, which I'm going to call dy, the displacement in the Y. Now, here's the thing. We know that the initial position is 10 meters, and the final position of where it hits me in the head is actually 1.8 meters. So the displacement in the Y is the difference of these two numbers. So that is the dy2 minus the dy1, or 1.8 minus 10, which works out to negative 8.20 meters to 3 sig figs. What's the other information that we know? Well, we know that Tom drops it. So the initial speed of the balloon, Vy1. So normally we'd just call that V1, but it's on the y-axis, so I'm calling it Vy1. And that's an initial speed of 0 meters per second because he dropped it. He didn't throw it, he dropped it. Okay, so now we have two pieces of information that are known so far. 1 and 2. You need a third in order to do any calculations. And that third piece of information wasn't stated in the question, but it always exists. And that is the acceleration due to gravity. And the acceleration due to gravity is negative 9.8 meters per second squared. Okay, so the good thing about that is now that we have 3 known things in the y-axis, we can find out what the other 2 are going to be. So what I'm going to do is I'm going to pop back up into the given section, and I'm going to start filling this information. So I'm going to break up my given section into the y-axis and the x-axis, and I call it the y component. So I've got dy, vy1, vy2, acceleration in the y, and t in the y. So we know that that is negative 8.20 meters. The vy1, because it's being dropped, is 0 meters per second. And we don't know what the vy2 is, and we know what the acceleration is, and that's negative 9.8 meters per second squared. And that is always true on Earth. So we have 3 things. The 2 things that we don't know is the final speed of impact, the vy2, and we don't know what the time is. Now onto the x component. Now with the x component, it's constant motion. So there's d, v, and t. But we have to put the subscript x to indicate that we're talking about the x-axis. And we know that my speed is, well, we're assuming I'm walking in the forward direction. and that's 2.50 meters per second. What we're looking for in this question was, again, how far in advance. So that's actually the dx is what we're looking for. So under the RTF, I'm going to write dx. Well, there's a problem. And the problem is this. In order for us to be able to solve for dx, I need two things. I need the speed, which is what we have, but I also need the time, which we don't. But here is the thing. And you can't solve this problem without understanding this idea. And the idea is this, is that the time it takes for me to walk from this position here to this position here has to be equal to the amount of time it takes for the ball to fall from here to here. So the takeaway is this, is that the time for me to walk along the x-axis has to be equal to the time the water balloon falls along the y-axis, which we're simply just going to call t, because the t and the y and the t and the x are the same time. So we're going to update our given section. So ty is equal to t and tx is equal to t. So in order to find dx, we have to find t. And to find t, we're going to have to look at the y component. So let's move on with our solution. So we'll take that diagram and label it as such. Next, we're going to find time using the y component. All right, well, that being said, we've got dy, vy1, acceleration, and we're looking for time. So we want to find the one equation that doesn't have vy2 in it. And really, vy2 is just v2. Well, let's find all the equations that do have it. That's got a v2, there's a v2, 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 and delta v means that there's a v2 as well. So that's the one right there. Now I'm going to modify it so that I have the subscripts. Specifically, I like having those subscripts because I want to make sure people realize that we can only use information that is relevant to the y-axis, not the x-axis. So this is dy is equal to vy1t plus 1/2 ayt squared, ayty squared. Okay, so now, since we're solving for time, I have to inform you of something ugly, t squared. Oh shoot, I forgot the subscript on my t in the first line there. It's a common thing that I do. Let's try that again. We have a ty term, a t term, and a t squared term. I know it's ty, but the y just means y-axis. Okay, so when you have a t term, a t squared term, and a non-t term, this means that we are in a situation where we have a potentially have to use the quadratic formula. Well, I have some good news for you, and that has to do with vy1. vy1 is 0. It's at rest. See, vy1, 0 meters per second. So that means this whole term goes to 0. So all of a sudden, we went from having a quadratic formula to not. So dy is equal to 1/2 ay ty squared. We're going to isolate for ty, and we're going to do that by removing the 1/2, the ay, and the ay first. Because again, and I know I sound like a broken record, it's all about SAMDEB. Now, there's no addition and subtraction. There's just multiplication and division at this point. So 1/2 is the same as divide by 2. So the opposite of divide by 2 is multiply by 2. So that's 2 dy. And the ay is attached through multiplication. The opposite of multiplication, division. And now exponents. So to get rid of the square, we take the square root of both sides. And now we can substitute in. So I'm going to turn the equation around at the same time. So my ty is just equal to t. And the dy is negative 8.2. And the acceleration on the y is negative 9.8. Okay, so now here's the thing. This is why you have to get your directions right, because you can't take the square root of a negative number. So if you forget the negative on the displacement in the y, or you forget the negative on the acceleration, bad things are going to happen. Here's the other point I want to make. We don't actually need to fully calculate the time. We're just going to simplify this inside the bracket, inside the square root, and then I'm going to substitute the square root in the next part of the equation. That way we just have a little less rounding. All right, so our time is the square root of 16.4 over 9.8. I mean, you can calculate it, but it'll add rounding error. So it's just as easy to use this in the substitution in the next part. Now, technically it's plus or minus, but since time can't be negative, we just work with the positive. Now we're going to find dx. And since it's constant motion, there's only one equation, and we're going to use dx equal to vx times tx, but tx is equal to t, which is equal to the square root of 16.4 over 9.8. So now we can substitute in 2.5 times the root of 16.4 over 9.8, and that works out to 3.23 meters. Therefore, the balloon must be dropped when LaRusso is 3.23 meters away from the target. And that's it. Up next, question 4. All right, kinematic sample problem number 4. So here's what we got going on here. This particular question is what I refer to as an object A, object B problem. So we have two individuals. We have Tom and we have Phil. And what they're doing here is they want to test out their new football helmets. These are actually two former students from many, many years ago. They didn't actually do this, but it was kind of hilarious to think that they would, because they were the kind of guys that would. To do this, they decided to run towards each other at a speed of 3 meters per second and 5 meters per second, respectively. Now, what that means is the word respectively simply means that the first number, 3 meters per second, refers to the first individual that I mentioned, that was Tom. And then the second number would be associated with Phil. So Tom is moving at a rate of 3 meters per second, and Phil is moving at a rate of 5 meters per second. Now, they're running towards each other. What I did not mention is which way either of them are running, and it actually doesn't really matter in this particular question. So by convention, I simply will assume that Tom was running forward or to the right, and Phil was running backwards or to the left. So I generally work with left and right because it makes most sense when you're looking at your diagrams. There's another couple of things that we have to see. So let's actually make a little list. So our first assumption was Tom is running to the right and Phil is running to the left. They are both running at their respective constant speeds. In other words, they're not accelerating throughout. We're assuming that they are running at that rate from beginning to end. And now, the only way to solve this problem is you have to make this final critical assumption. They both start at the same time. This implies equal time for both of them. That one little point here, without that assumption, the question becomes unsolvable. And the reason why is if they started at different times, there are actually an unlimited number of solutions to this problem. So they could meet pretty much anywhere in that space between them if we don't assume that they both start at the same time. And that's one of the toughest things when students are first learning how to solve physics problems, because there are so many assumptions that are sort of implicitly made, not explicitly stated, but the expectation is that you would come to these on your own, which, I find maybe a little bit unreasonable, because generally speaking, when students are new at these sort of things, these are not things that they would necessarily think about. So I will do my best to point out these particular common assumptions, and hopefully that will set you up for, when you move on to grade 12 and post-secondary. But a lot of these questions, they have to make these assumptions. Now, the one last piece of information that we know is that they are 30 meters apart. Okay, so now that 30 meters apart is the total distance that's separating both of them. That doesn't mean both are running that full 30. No, each of them are running part of that 30 meters. And when we draw the diagram for this, it'll be much easier to parse exactly how that 30 meters comes into play. So I'm just going to simply refer to that as D-separation or D-sep when I put it inside the given information. But that being said, when we make our givens, I'm actually going to break up my givens in terms of Tom and Phil. All right, so since both of them are running at a constant rate, we're going to be using the kinematics formula for constant motion, which only has 3 parameters: distance/displacement, speed/velocity, and time. So each of them will have their own set of data, of information, of those parameters. Here's the problem. If you look at the way I've drawn the symbols, there is no way to distinguish between Tom and Phil. So I'm going to add subscripts. T for Tom and P for Phil. Now, in these questions, these are technically vectors, but what I'm going to do is I'm going to represent the direction of the vectors in scalar form because they're collinear, because they're both running on the same line. They're going left, right. So that means I'm going to represent Tom's velocity as positive 3 because we're assuming he's running to the right. So that's positive 3.0 meters per second. Where Phil, since he's running to the left, he's running at 5 meters per second, but negative because negative means to the left and positive means to the right. These are kind of key things. You must get the signs correct. Now, as it's set up, we only have one piece of known information. The other piece that we have in here, which we haven't discussed yet, is the separation distance, which is 30 meters. Now we're gonna approach that in a moment. I'm just gonna leave that as D-sep for now. So that's just representing how far apart they are. Next, when we take a look, we got Tom and Phil. There's one other point, and if you recall up here, that's this point right here. Equal time for both of them. So I'm going to say let time for Tom equal to T and time for Phil also equal to T. I don't know what the T is, but I do know it's common for the both of them. So at the moment, if we look, we have 1, 2, and well, we had 4 unknowns, but now these 2 unknowns are the same. So that is a third unknown. If you recall from every previous math course you've done, to solve an equation, you have to get it down to a single unknown. At the moment, we have 3. This is how we're going to address the last 2 unknowns. And that's where this D-separation comes in. So with the diagram, I know Tom, or we're assuming Tom, is running to the right. So I'm going to have him here on the left-hand side. And then Phil is over here on the right-hand side. This blue line represents that separation distance of 30 meters. So we know that they're separated by that amount. So each of them, combined, their distances the combined distance that each is going to run will cover the full 30 because Tom is going to run part of it, Phil is going to run the other part, and they're going to meet somewhere in the middle. Now let's talk about things logically here. So when we talk about how far each are going to run, it should be fairly obvious that since Tom is running at a slower rate than Phil, the meeting point will be closer to Tom as opposed to Phil. So it won't be right in the middle. It'll be somewhere over here. Well, maybe not quite that close. Yeah, that's more realistic. All right, so I don't know where this position is. That's actually one of the things we're asked to find. So we're looking for the position X. So here's the next little trick. I'm going to treat this like a number line, i.e., if where Tom is standing is at the origin of a Cartesian plane, i.e., if this is like your X and Y axis. So the y-axis isn't important. It's all the x business. So what we're going to do here is we're assuming that Tom is the starting point. Do you have to do it that way necessarily? No, it just makes more sense, and we can avoid negative signs, unnecessary negative signs, of course, if we do it this way. We could make Phil the 0 point, but then Tom's position would be negative, and that's just less intuitive to do mathematically. That being said, I'm going to say Tom's position is at the 0 meter mark. And that means Phil is at the positive 30 meter mark right here. So the next little bit of info is now we can actually talk about the rest of the information from each of these fellas. What I'm going to do here, and what I also expect you to do, is I want this given information up here labeled on the diagram every single time. It may seem redundant, but it is always best practice, and mostly because you run into less risk of missing important points. Now, time to fill in the distance for Tom, or the displacement for Tom, and the displacement for Phil. Now, Tom is running to the right, and Phil is running to the left. And I'm going to do a modification to my diagram. I'm putting, to my best of my ability, evenly spaced dashed lines. It's not perfect, but you get the idea. But for Phil, I'm going to make the dashed lines bigger. And that is to indicate the idea that Phil is running faster than Tom. So I often will communicate the the speed or the velocities or the velocity change by how long I draw the dashed lines. Okay, so now let's take a look. I know displacement is the final position minus the initial position. Let's try that again. The final position, there we go, minus the initial position. Okay, now this step here, I don't expect you to actually write this step, but since I'm explaining and teaching the concept, I'm going to write that down at the moment. I'm about to erase it, but I do want that idea in your mind that it is the final position minus the initial position. So the final position is x, and the initial position is 0. So x minus 0. Now, when you look at that number, that's going to turn out to be a positive number because x is going to be a positive number, minus 0 is still going to be a positive number. And that makes sense because Tom is running to the right. Now, let's take a look at Phil. Phil, his final position, so dphil 2 minus dphil 1. So the position of Phil at the end minus the position of Phil at the beginning. Well, he also ends at x, but Phil's initial position is 30 meters. So that means minus 30. And the big idea here is that Phil's displacement has to be negative, and that is going to be negative because x is going to be smaller than 30. So a smaller than 30 number minus 30 has to give you a negative number. So the direction here is totally in line with how he is running. Oh, and we forgot to figure out our RTF. Well, that was silly. So for part A, we're asked to find the time. And for part B, we're asked to find the displacement of Tom and Phil. Well, actually, technically, nope, it didn't actually ask for their individual displacements. It just asked where they met. All right, nice little glitch there, OneNote. So we're looking for x. Okay, so now let's talk about how we've reduced the number of unknowns. By doing these little steps, x is unknown and t is an unknown. And that's the same x and t over on Phil's side. So right now we have two unknowns. Well, if you recall from grade 10 math, when you have two unknowns, you need a grand total of 2 equations. Therefore, we are going to generate 2 equations, and one is going to come from Tom, and the other is going to come from Phil. So the equation for Tom, and since Tom and Phil are both running at a constant speed, we're using the constant motion equation, and we're using it in this form. D is equal to V times T with these subscripts. If you do not put in those subscripts, bad things will happen to you academically. And now what we can do is we can fill in what we know for each of these in terms of the values that are represented in the given section up here. I'm just going to put a little separation line here. There, that's a little prettier. Okay, so the displacement of Tom, that's just equal to x. And we don't need the minus 0, of course. V Tom, that's going to be positive 3. And I'm dropping the extra sig figs for now because it doesn't help us do the algebra. Just we have to remember at the end, we have 3 sig figs we started with. We're going to end with 3 sig figs. And the time for Tom is just t. That is equation number 1. Now we go over to Phil. So for Phil, that's d Phil is equal to v Phil times t Phil. Now the displacement of Phil, that's going to be x minus 30. And the speed of Phil, or the velocity of Phil, is negative 5t. OneNote glitched out on me again. Sorry about that. Negative 5t. There we go. You know, Microsoft people, if you're watching this, which I highly doubt, but if you are, could you please fix that stupid annoying bug in OneNote where it doesn't actually commit what you draw and you don't know until you try to scroll? It's kind of annoying. Anyway, I digress. Next, we could actually leave it at this and then call this equation 2. But I find that grade 11 students are more comfortable if I isolate for x on this side, which is an easy thing to do. I mean, whether you do it now or you do it later, it's not a big deal. All right, so now what I'm going to do is I need to get x by itself, which means I have to remove this negative 30. Well, again, let's go back to our good friend SamDeb. And we always use SamDeb when we're isolating. When you're expanding, you use BEDMAS, but when you're isolating, you're using BEDMAS in reverse. So that's SamDeb. So we have to do the subtraction addition. So since that is minus 30, it becomes plus 30 when it goes onto the other side. And that is our equation 2. So the next thing we're going to do is we're going to set the equations equal to each other. So in this case, I'm going to set equation 1 equal to equation 2. We could have done 2 equals 1, but the reason why I did 1 equals 2 is I'd like to have my variable on the left side of the equation, and I would like it to be positive. So as you can see, this is positive, but this is negative over there. As a result, I'm going to eventually have to bring this negative 5t term to the left-hand side, and I just prefer things to be positive. Again, there's no law saying that you have to do it this way. I'm just recommending it. Okay, so we have 3t is equal to negative 5t plus 30. So again, we're going to collect like terms. And here are our like terms that we are going to collect. I'm going to bring this negative 5t, I'm going to bring it to the other side. And of course, using SAMDEB, the opposite of subtraction is addition. So this is going to be 3t. I don't suppose we have to keep on carrying the positive there. Plus 5t is equal to 30. 8t is equal to 30. So t is equal to 30 divided by 8, because again, 8 is attached through multiplication. The opposite of multiplication is division. So our time is 3.75 seconds. So therefore they meet in 3.75 seconds. The next part is that we have to figure out where. And that where refers to x. All right, so now here's the thing. To solve for x, we can either use equation 1 or we could use equation 2. I'm going to argue that equation 1 is probably the cleaner one to use, but regardless, we're going to have to use our value for time. So this is one of those situations where you have no choice but to work with one of these found values, which is the value for time. Now, as it turns out, that 3.75, we didn't have to round it. That is actually 3.75. So we should end up with a fairly clean result. So we're going to sub t equals 3.75 seconds into equation 1. And again, you should always start with the equation before you substitute in. That is an expectation. And the answer is 11.25 meters. So they meet at 11.25 meters to the right of Tom's starting position. Easy as that. Oops, apparently not easy as that. I forgot one small little detail. I did mention at the beginning of the question that we have to have 3 sig figs. So the time has 3 sig figs, but this, well, that's 4 sig figs, and we have to round it down to 3. So it is not 11.25 meters, but that would actually be 11.2. So 11.2 meters would be the correct amount. And the reason why it's 11.2 and not 11.3 is because of banker's rounding. Question 5. This is another example of an object 1, object 2 type problem. Similar to Tom and Phil, that we have 2 individuals that are running at a constant rate. But in this case, they're not running towards each other, they're running in the same direction. To add to the complexity, there is a time delay. So let's take a look at what's going on here. A boy runs out the door and starts down the road towards school at 10 kilometers per hour. Now, normally we use meters per second, but in this question, the units were given in kilometers per hour, so we're actually going to work in kilometers per hour. 6 minutes later, his mother discovers that he has forgotten his lunch, and she runs after him at 14 kilometers per hour. Now, this is quite the fit family here. I always find it hilarious when I think about what the numbers are after the fact. But apparently we have a family of Olympians over here. Okay, so this boy who's running probably at my top speed is en route to school at 10 kilometers per hour. Then there's a 6-minute delay, and then mom heads out after him. So how far does he get in 6 minutes? I also put a little space in there. And we want the answer in kilometers. All right, so as you can see, what I'm doing here is I'm highlighting things, the given information in one color, and then I'll highlight what we're asked to find in another. So how long does it take her to catch him in minutes? Okay, no new numbers there. And how far? Okay, so far, here's the numbers. We've got a speed of 10 kilometers per hour associated with the boy. We have a 6-minute difference between when the mom starts and when the boy starts. And we have a speed of the mom. which is 14 kilometers per hour. So what we're going to do is we're going to do something very similar. We're going to break everything down in terms of mom and the boy. So in our given sections, we have information about the boy and information about mom. The other important thing to note, and it is an assumption, is that both are running at constant speeds / velocities. So again, we're going to default to working with the vectors, and I'm just assuming that they're all going in the forward direction, or to the right if you prefer. It doesn't really make a difference. But we're going to be using positive and negative to represent these directions because everything's collinear. So again, D, V, and T. However, we have to distinguish these from mom, hence the subscript B. All right, so now what we know about the boy is that he was traveling at 10 kilometers per hour. And we kind of don't know anything else at the moment. Well, that's not entirely true, but we have to do a little bit of interpretation. And we'll do that as we go along here. So let's talk about the mom now. We have the displacement of mom, the velocity of mom, and the time for mom. We know that mom is running at 14 kilometers per hour, both in the positive direction. So the things that we don't know is the displacement for the boy and the mom, and the time for the boy and the mom. But there is a relationship between the time for the mom and the time for the boy. And that has to do with this 6-minute head start. Okay, so now we need to think, who gets the head start? Was it the boy or the mom? Very obviously, it was the boy. So what that means ultimately is that the boy runs 6 minutes longer than what the mom runs. So the boy is going to have more time. The other issue is this. In our unit, the time is in hours, but this time has been given to us in minutes. That should, raise alarms when you see a discrepancy in units. So what we're going to do is we're going to get the units to agree. We're going to be working with kilometers per hour, which means that 6 minutes, I'm going to want to convert to hours so that we're all on the same page. So I'm just going to represent that in the given section. And I'm going to call that THS, which stands for the head start. So that is 6.00 minutes, but we need to convert that to hours. So if you want to convert minutes to hours, you divide by 60 seconds. No, let's try that again. 60 minutes in an hour. So we have to divide this 6 by 60, and that gives us 0.100 hours. Keeping the same number of sig figs. Okay, diagram time. And what I'm going to try to do is I'm going to try to recreate this sort of, not in real time, obviously, but this sort of idea of what's going on. So this path here is going to be what the boy is doing. And over here, this is mom. And I'm getting a little ahead of myself because actually there's a couple of methods. There are a couple of methods to solve this problem. So we're going to go through those various methods. So this first method is from the perspective of equal times. So that's the first method that we're going to do, the perspective of equal times. So let's take a look at the first 6 minutes. So for the first 6 minutes, the boy is going to cover some ground. And this refers to the distance of the head start. And we know that the time for this head start is equal to 6 minutes or 0.100 hours. And then at that point here, like that point there, when the boy reaches there, then the mom starts. So she's on her way. So with this perspective, we are restarting the stopwatch, which means we're starting the time now. So when the boy is here and when the mom is here. And that's where the title, Perspective of Equal Times, comes into play. The distance that the boy now covers from this moment on is going to take the same amount of time for the mom to cover that full distance from home. So the idea we got going on here is that they're going to meet somewhere over here. And this little section here is how far the boy runs in that time. And this is an unknown value. So what I'm going to do here is I'm going to dash the lines. I do wish I could draw these spacings a little bit more consistent, but again, this is to represent the boy's constant speed throughout this section here. Now, the distance in this section, and you know what, I'll just highlight this in green. that is unknown. Now let's take a look of what's going on with mom. Now mom is starting all the way from home, and I'm going to draw her dashed lines longer to give the impression of her higher rate of speed. Okay, so now here's the thing. The boy covers the distance x in the same amount of time that mom covers that head start distance and x. So the mom's got to cover all of this in the same amount of time. Okay, so we're getting a little ahead of ourselves here, but I wanted to sort of talk it through with the diagram first before we get into all that detail. So let's go back up top here and figure out our givens. So first of all, for part A, we're looking for the distance of the head start. For part B, we're looking for the amount of time it takes for mom to catch up. That's the how long. And we do want the answer in minutes. But since we converted everything to hours, we'll have to do the conversion back. So we're looking for time, mom, and part C. How far from home is he when she catches him? So that actually is not a measurement of how much he's run. Well, technically, it's the X distance that he runs plus the distance of the head start. But the mom actually covers that entire distance. So this is actually asking for the distance of mom, or the displacement, really. Okay, so we got that. All right, so we're good. All right, so let's do part A down here. So we have to find the distance of the head start. Well, the distance of the head start, that's associated with what the boy is doing. So we're going to find the distance of the head start, and that is associated with what the boy is doing. So the distance that the boy travels during the head start is equal to the speed of the boy, or the velocity of the boy, times the time of the head start. So that's going to be 10, actually positive 10 times 0.1, and that works out to 1 kilometer. So what we're going to do here next is I'm going to restate all my given information, but I'm going to do it with a diagram, just like I did before. So now I'm going to put the boy's information over here to the right. So now I know the following thing. And again, everything is happening between these respective red lines. So the time we're talking about right now is between this red line and that red line for the boy, and this red line and that red line for the mom. So over here, the distance of the boy. So during this segment, because this is happening after the head start, we're restarting our stopwatch. The distance that the boy runs is just x, but the distance, or really the displacement of the mom, that's going to be the x plus the distance of the head start, which is equal to 1 kilometer. Now, the speed, or the velocity, I should say, of the boy is positive 10 kilometers per hour, and for the mom, positive 14 kilometers per hour. But now the final thing, the time for the boy is equal to the time for the mom, equal times, which is just equal to t. Great. And now it's time to make the equations for both the boy and the mom. So again, constant motion, d is equal to v times t. And I've already made a mistake. This time it was actually on purpose, not like my normal mistakes, which are totally accidental. I'm missing something. What am I missing? Yes, correct, the subscripts. And we have the same equation for mom. Now, at the moment, in these two equations, we have a total of 1, 2, 3, 4, 5, 6 unknowns. As we start substituting in those things that we found, we're going to reduce the total number of unknowns. And ultimately, we need to get down to just one unknown. Okay, so let's talk about the boy. So we know with the boy, we know the distance that the boy runs is x, and the speed of the boy is 10, and the time for the boy is t. So x plus 10, positive 10, I should say, times t. Okay, so we now have two unknowns. That's technically positive x, but I don't think that's actually necessary. Now, what the heck? Just be as specific as possible. Now, for the mom, that's x plus 1 is equal to positive 14 times t. Okay, in these two steps, what we have done is we have reduced it down from 6 unknowns down to 2 unknowns, and that's x and t. So x is equal to 10t, and I'm going to call that equation 1. I just dropped all the extra stuff. Now for mom, I'm going to bring that plus 1 to the other side. So that's going to make it x is equal to 14t minus 1. And that is my equation number 2. All right, so the next thing, we're going to set them equal to each other. So again, here's the thing. Do I want to do 1 equals 2 or 2 equals 1? And here's the thing that try to keep in mind. I want the variables to be on the left-hand side, and I want the variables to ultimately be a positive number. So if I put 1 on the left-hand side, I'm going to have to bring that 14 over, which makes it negative, which will make it a negative number. So I want it so that the bigger of these two numbers is on the left-hand side. So I'm choosing 2 equals 1. Again, not a huge deal, but it just saves one small step at the very end. Okay, so that's going to be 14t minus 1 is equal to 10t. Again, doing SAMDEB. We're going to do two things at once. I'm going to take that subtract 1 and I'm going to bring it to the other side. And the opposite of subtraction is addition. And I'm going to take this positive 10 and bring it to this side, and that will become a negative. So this gives me 14t minus 10t is equal to 1. Combining like terms, that gives me 4t equals 1, t is equal to 1 over 4, t is equal to 0.25 hours, which equals a quarter of an hour, which is 15.0 minutes, 3 sig figs. And my minutes look like millimeters. Let me try that again. That's better. All right. So they meet after 15 minutes. Actually, hold up. The mom takes 15 minutes to meet up with the boy. But the boy already had a head start of 6 minutes. Remember that. So for the boy, this is an additional 15 minutes from that an original 6 minutes. So from his perspective, he's been running for 21 minutes. All right. So therefore, the time for mom is equal to 15 minutes. So the next thing we need to do is we have to figure out how far she went. So we know that the distance of mom is equal to the speed of mom times the time of mom. And that's going to equal positive 14 kilometers per hour times, now you don't put in 15 minutes. You have to put in the 0.25 hours. And the reason why is because that 14 kilometers per hour is per hour. So the units have to match 0.25 hours. And that works out to 3.50 kilometers. Therefore, mom ran 3.50 kilometers. Okay, great. Well, that was our first method. Now we're going to try a second one. Method 2, the perspective of equal distance. So we're now not talking about equal times, but we're talking about equal distances. How does that look any different? Boy, mom. They meet over here somewhere. And both the boy and the mom are running the same distance. They're both started from home, but the boy is running at a slower rate. Hence, his lines are dashed much more closely together to indicate that he's going a bit slower. This time, we're not worried about the distance as a head start. The time, I should say, let's try that again. This time, we're not worried about that distance head start. We're actually concerned about the time head start because we're measuring the distance with respect to home. So what this means is that both the mom and the boy are running the same distance. Okay, so let's see what that looks like. So the distance / displacement of the boy, let's call it x, technically positive x, because Buddy is running in the forward direction. Buddy's velocity is positive 10 kilometers per hour. And then I'm just going to leave the time for the boy alone for the moment. Let's go back to mom. Her displacement is also positive x. Her velocity is positive 14 kilometers per hour. And then we have the time, which are not the same. The times are different this time. The question is, who had more time? The mom or the boy? The answer, the boy. Because the boy had a 6-minute head start. And remember, the head start of 6 minutes is equal to 0.1 hours. So if the mom's time is t, for the sake of argument, then the boy's time is going to be t plus 0.1 hours. And I'm just going to write a little note. 6 minutes is equal to 0.1 hours and also 3 sig figs. Okay, now time to commit to our equations. So we have displacement of the boy is equal to the velocity of the boy times the time of the boy. And the same is true for mom. Now again, we don't have the vector notation up there. I realize that. That's because we're using collinear vectors and we're using positive and negative to represent the directions. So the displacement of the boy is x. The velocity of the boy is positive 10. And the time for the boy is going to be t plus 0.1. Now, we're going to clear out that bracket. It's looking a little messy in there. So using distributive property, that's going to be 10t plus 1. Because 10 times 0.1 is just 1. Okay, so for mom, the distance slash displacement is 14. It's x, sorry. The velocity is positive 14. And the time is just equal to t. Equation 1, equation 2. We're going to set them equal to each other, and we're going to do the exact same thing we did before. I'm going to do 2 equals 1. So that gives me 14t is equal to 10t plus 1. Bring that 10t to the other side, becomes subtraction. 4t equals 1. T is equal to 0.25 hours, which is 15.0 minutes. It's the exact same answer as we did before. All right, so it doesn't matter which way we do it. We're going to get the same answer. However, there is a second way that we actually could have done method 2, which I kind of want to point out, because the second method that we use, that we could have used in method 2, may confuse some folks. So here is what I'm going to do. I'm actually going to copy the solution that we just did, and then I'm going to modify it. So here we go again. It is method 2, but this is going to be an alternative setup. Now, the reason why I'm saying it's an alternative setup, because the way I argued about the time, we could have argued it differently. The way we did it is I said that the time of the boy was 6 minutes longer than the time for mom. So that meant I had the time for the boy was t plus 0.1. And that's what I did up here. But we could have looked at it another way. We could have said, hey, let's say the time for the boy was t, and the time for mom is going to be t, but less 6 minutes. So t is whatever the time that the boy had, minus 6 minutes, which is 0.1. And this should give us the exact same answer. It should, but will it? Well, let's find out. Okay, so d boy is equal to x. V boy, 10. T boy, t. Okay, d mom, 14. I should probably put my plus. Now, what am I doing? Oh, good gravy. Good gravy. Sigh. All right, let's try that again. D mom is x. There we go. V mom, positive 14. And then the time for mom is t minus 0.1. Okay, so we got to clean up mom's equation here a little bit. So that's going to be x is equal to 14t, because we're using distributive property, minus 1.4. Uh-oh. We didn't see a 1.4 last time, did we? We're going to do the same thing we did before. Equation 2 equals equation 1. So equation 2 is x is equal to 14t minus 1.4. Equation 1 is 10t. Collecting like terms, we're going to bring the 10 to the other side, and we're going to take that negative 1.4 and bring it to the other side. And of course, using SAMDEB, we're using addition and subtraction to do that, so that the signs are going to flip. So we get 14t minus 10t is equal to positive 1.4. We are not getting the same answer. Okay, so the last time we got 0.25 hours, and now all of a sudden we have 0.35 hours. What gives? Nothing. In fact, this is correct. What you may not remember is that in this case, this letter T is not the T for mom. This is the time for the boy. And if we convert 0.35 hours into minutes by multiplying by 60, that gives us 21 minutes, because this is actually the time for the boy, which is equal to that 6-minute head start plus the additional 15 minutes that he had to run before mom caught up with him. And that's a total of 21 minutes. So in fact, this method does give you the correct answer. You just have to remember that it was from the perspective of the boy, not the mom. And even though I'm not going to bother to do it, but if we find the value for x using this formula here, x is equal to 10 times t, and we use the 0.35 hours, 10 times 0.35 is 3.5 kilometers, which is how far it was in the previous question. That's how far away from home they were when they met up. Okay, so now I did it 3 different ways to solve this problem. You would never be expected to do all 3. You just pick one of them. And you pick the one that makes the most sense for the question, or the one that at least makes the most sense to you. So there are 3 versions. Question 6. This question is very similar to a Tom and Phil type question, whereas we have both objects moving towards each other. Well, in this case, we have 2 kids that are running towards each other. Kid A is running to the right at a constant speed of 3 meters per second. All right, so there's Kid A and constant speed of 3 meters per second. This sounds a lot like the Tom and Phil question because Tom was also running at 3 meters per second. Kid B starts running at a rate of 1 meter per second. Oh, starts running at a rate of 1 meter per second, but is accelerating, there we go, at a rate of 0.5 meters per second squared, all towards the left. Very important, all towards the left. If they are initially separated by 100 meters, determine the time for the collision and the distance covered both by Kid A and B. So again, we are looking for the time and the distance / displacement of Kid A and Kid B. There's a lot of ands here. Let's clean that up a bit. All right. And I use the Oxford comma too for good measure. Okay, so this is similar but different. And how it is different is that one of the kids is accelerating, which means that we have to now move to those accelerated motion kinematic problems, equations, I should say, for Kid B, because Kid B is experiencing accelerated motion. So Kid A, just constant motion. And you notice I always use the d is equal to vt form. And the reason why I use that one, because that one is actually in a similar style to all the accelerated motion kinematic equations. So again, a few assumptions. Kid A is experiencing constant motion throughout. So no acceleration whatsoever. So we're assuming that Kid A starts and continues at that 3 meters per second, i.e. that means equal time for both. Should probably read the whole sentence there. Try that again. Both kids start at the same time, i.e. equal time for both. And that's mission critical that we have that one particular point. So again, Kid A, constant motion throughout, no acceleration whatsoever. Both kids start at the same time. And of course, from a physics point of view, it is impossible if they started from rest. So we're assuming that they're not. So the time that we're talking about is from when they are 100 meters apart until they meet. So for Kid A, only one possible formula. But for Kid B, we have a total of 6 that we could choose from. Technically 5, because 2 of them are just a rearrangement of the other. So we're going to paste that list over here on the side, and we'll refer to that as we come along. So that's what makes this question a little bit more complex, is that we have all of these to work from with Kid B. But we're going to pick the specific one that is relevant. And again, that's why it's mission critical that you set up your givens properly. So let's start off with Kid A. Again, since our first kid here is moving at a constant rate, the formula is very simple. Only 3 kinematic parameters. So the velocity of Kid A, and this time, since it did give it to us with directions, I'm, at least in the given section, I'm going to write it as the direction. 3 meters per second to the right. And that's all we specifically know about Kid A. Let's take a look at Kid B. Now for Kid B, there are a total of 5 kinematic parameters that are relevant. So let's start in order. Kid B starts running at a rate of 1 meter per second, but is accelerating at a rate of 0.5 meters per second squared, all towards the left. So we know it's to the left, so we know it's going to ultimately be negative. So that 1 meter per second squared, this right here, what is it? Because we know it's a speed, or a velocity, I should say, because of the units, meters per second squared. So that is either VB1 or VB2. And the key word, starts. That makes it VB1, and it's to the left. Now, The next thing we know is the acceleration, which is 0.5 meters per second squared, also to the left. So far, so good. Now, we don't know d, v, v2, or t for kid B. So when we do an inventory of things that are unknown at the moment, we have dA, TA, dB, VB2, and TB. That's 1, 2, 3, 4, 5 unknowns. We eventually have to get it down to just one. One of these unknowns, specifically for kid B, will naturally be eliminated because our kinematic formulas for accelerated motion only require 4 out of the 5. So the big question is, which one are we going to exclude? Will it be the dB, VB2, or TB? And here's how we make that decision-making process. Or I should say, this is how we go through that decision-making process to ultimately come with that decision, or to that decision. Good gravy. Grammar fails today. All right, so let's circle back to this unstated but critical assumption, equal time for both. That means TA and TB are equal to T. All right, so now the fact that both TA and TB have a unknown in common, we know that the formula that we're going to choose for kid B must incorporate the letter T. So next, we have to decide if the equation that we're going to work with for kid B is going to exclude dB or exclude VB2. Well, there's one other piece of information that we haven't put in our given yet, and that is the distance separation. So the d-sep is 100 meters. What that means is the distance, and I am actually intentionally using distance. The distance that kid A runs combined with the distance that kid B runs does add up to that 100 meters. So we know that there's actually a relationship between the two distances. So the big clue is, since we have information about distance, that is not the variable that we want to eliminate. So the variable we're going to eliminate is VB2 because there is no connection to anything else in this question. The fact that we've eliminated VB2 because we've established that we're going to be working with dB, VB1, AB, and TB tells us immediately that we know which formula is going to be involved in this. And it is the one formula that doesn't have V2 in it. And if you look, the only formula that does not have V2 is equation number 2. Every other formula has a V2 in it. And don't forget, delta V is V2 minus V1. All right, so those are the two formulas that we're ultimately going to work with. So now we have a few more things that we have to work with here before we can go any further. The next step is we really do need to have a proper diagram to help us out. So kid A is running to the right, which means we have to have kid A on the left-hand side. Over here, we have B. So we know that they're separated by 100 meters. Now the tricky part, it was easier for the Tom and Phil question to guess where our meeting point was going to be. And the reason why is because Phil was running faster. So Phil covered more distance. It was very obvious. The problem is kid A starts off moving more quickly. So kid A's initial speed, the kid A's speed, or velocity, I should say, is a constant rate of 3 meters per second, where kid B initially starts at 1 meter per second, but is accelerating at 0.5 meter per second. So even though kid B is going to be covering less ground at the beginning, kid B is also speeding up. So kid B might actually cover more distance ultimately. It's kind of hard to tell. So when you do a question like this, you kind of have to guess. You don't really have a choice. So what I don't recommend you guessing is straight in the middle, because I don't want you to make any assumptions that they're going to meet right in the middle. So I would either have it closer to A or closer to B. And really, it's a guess. And if you're wrong, it's cool. Why? Because the algebra will take care of it. So for the sake of argument, I'm just going to say closer to A. No, I'm assuming that kid B is stepping it up. So again, kid A is at position 0. That is position X, and this positive 100 meters. All right, again, so I'm copying all of that information from the given section, and I'm putting it by my diagram. And yes, I want you to do the same thing. Focusing on kid A, the displacement of kid A is going to be the final position minus the initial position. So that's going to be x minus 0. Now, over here, I'm actually going to eliminate right, and I'm going to make that value positive because they're collinear, and that means they're moving in the positive direction. For kid B, it's the final position minus the initial position, x minus 100. And for VB, I'm going to turn that left into a negative, and the same with the acceleration. Now time to make the formulas. Starting with kid A first, kid A is going at a constant rate, so that's going to be dA is equal to VA times TA. dA is equal to x, VA is positive 3, TA is equal to T. That's our equation 1. Kid B, dB is equal to VB1 times TB plus 1/2 AB TB squared. So x minus 100 is equal to negative 1 times T minus 1/2 negative 0.5 T squared. I made a small mistake. That's supposed to be a plus sign there. Sorry about that. All right, so let's do some cleaning. Now, you notice I didn't put the number 1 there because it's just going to be negative T. I mean, if you're more comfortable, I could leave it there, but all right, I'll put the 1 there. Fine. X minus 100. Now I'm going to drop it. Okay, so now let's clean that up. So that should be negative 0.25 T squared. Okay, so now get x by itself. All right. Now, let's take a look. We have our 2 equations, and we have 2 unknowns. I did mention that we want to get down to 1 singular unknown. So when we have 2 equations, 2 unknowns, we combine the equations. The question is, which way are we going to combine them? 1 equals 2 or 2 equals 1? I'm going to go with 1 equals 2 because I can see what is happening in this question where you might not yet. Although some of you should be getting a little pang of anxiety right now for recognizing something ugly that's about to happen. So I'm going to go over where I have some real estate. So I'm going to do equation 1 equals equation 2. So 3t is equal to negative t minus 0.25 t squared plus 100. Okay, so now, do you see where we're going with this question? We have 2 t terms, a t squared term, and a non-t term. Still don't see it? I'm going to bring everything to the left-hand side. And you're thinking, what? Why are you going to do that? Well, you'll see. I don't like that negative sign. So I'm going to bring it to the left-hand side. Yep, that's what I'm going to do. Fight me. Okay, so, but really don't fight me on this. It's actually a good idea. Because we don't need that kind of negativity in our lives, people. Now, I'm going to bring this t to the other side. So that's going to be positive 3t plus t. Oh, look at all this positivity. All right, but then I'm going to have to bring the 100. It becomes negative. Equals 0. Collecting like terms. And there you have it. This is a quadratic, which means that you're going to have to use the quadratic formula. That's correct. This is your life now. So all those things that you had to do in grade 10 that you thought, I'm never going to have to do again. Nope. You will be doing all of the things. So that's your A term, your B term, and your C term. Now, some of you are thinking, oh, can't we just use, regular factoring? No, because these aren't going to ever work out to a pretty number. Almost never, at least. So don't even bother try to do traditional factoring. Forget about it. Waste your time. You're just going to jump right into the quadratic formula and just deal. All right, so we're going to find t using the quadratic formula. I think we can zoom in a little bit now. Okay, so now here's the thing. You are so used to doing this. X is equal to negative b plus or minus square root of b squared minus 4ac over 2a. You're so used to doing it this way because, there's nothing wrong with what's happening on the right-hand side of the equation. My issue is that our equation has t's in it, not x's. So that's hilarious. I guess you can't really cross out an x. I guess I have to do that. That's not an x. humans of profound awesomeness, that is a t. So substituting in, and of course, you're going to get 2 roots from this. So you end up getting positive 13.54 seconds or negative 29.54 seconds. Obviously, time can't be negative, so our time is 13.54 seconds. So next, of course, we have to find our position x. So we have 2 choices of equations. We can use this one or that one. Yeah, I've made my choice. So x is equal to 3t, which is 13.54, which works out to 40.62 meters. But we need to find dA and dB. Well, we know that dA is equal to x because that's what we had as the original given there, which means that dB is x minus 100, which works out to negative 59.38. And now for the therefore statements. Therefore, they met after 13.5 seconds, rounding off to 3 sig figs, and kid A traveled 40.6 meters to the right, and kid B traveled, using ditto marks here, 59.38 meters to the left. Sample problem number 7. This type of problem that we're approaching next is something that I like to call a section A, section B type problem. Now, in the previous 2 examples that we did, we had 2 individual objects. One of them was kid A, the other one was kid B. We also had the question where it was the mom and the boy, and then we had the Tom and Phil type questions. Those are separate objects, so to speak. I mean, I realize they're people, but you know what I mean. They're separate objects. In this case, we have a single object that is falling, but it is doing 2 different things, or at least there are 2 different regions. So we have a flower pot that falls from a windowsill in a high-rise apartment. All right, now the key word is it falls, because believe it or not, that actually communicates some information to us. The pot falls past a window some distance below. So there is a window, and it's some distance below, and it passes by in 0.3 seconds. If the vertical size of the window, and this is the window below, is 120 centimeters long, determine the height above the window from which the pot fell. So we're looking for the height above the window. I can't really jump into the given section yet, and the reason why is that we need a diagram first. So I'm going to work a little bit backwards and, well, I guess in parallel, the givens and the diagram. Okay, so we're going to start off with representing our flower pot, and just as a simple circle. Now, some distance below, we have a window. Now, as mentioned before, the flower pot falls down past this window. Now, to indicate the fact that it's in a state of free fall, I adjust the dashed lines so they get larger every single time. So this is to try to represent accelerated motion. All right, so now here's where things come into play with this idea of the section A, section B. I'm going to label the stuff that happens above the window. I'm going to call everything that happens here section A. And everything that happens past the window, we're going to call that section B. So here's the thing. With section A and section B, it all pertains to the behavior of a single object, and that is object A. So now in the given section, I'm going to break everything up into section A and section B. And here are the big ideas. The flower pot is falling under the influence of gravity, which means it is accelerating. That means the 5 kinematic formulas, or 6, however you look at it. And that is displacement, velocity 1, velocity 2, acceleration and time for section A, and displacement, velocity 1, velocity 2, acceleration and time for section B. Let's go back to our diagram. And we're going to start filling in information that we know. Well, actually, before we do that, let's go back up to where we actually have some numbers. Okay, so first of all, let's talk about this 0.300 seconds. That is the distance, that is the time, I should say, because it's in seconds, that it falls past the window below. So that means this 0.3 seconds refers to what happens here past the window. So that means the time for section B is 0.300 seconds. The next number that we've been given is 120 centimeters long. That's the width well, I guess the height of this window. So that 120 centimeters refers to this. So now, of the kinematic parameters, and I really should put that number in there. All right. So of that 120 centimeters, that gives us some information about one of these kinematic parameters. Displacement, V1, V2, acceleration, or time. Well, that 120 is actually how far the object falls when it's falling past the window. So that 120 centimeters works out to be the displacement. So what I'm going to do over here is I'm actually going to put all the parameters here so we can see what we need to find and what we have. So first of all, we're going to convert that into meters. Oh, it was originally 4 sig figs. So we'll keep it as 4 sig figs, and I'm going to write the following number down, and I'm going to tell you that that is actually incorrect. And I purposely wrote it down wrong, and it wasn't a conversion. It is 1.200 meters. The problem is the direction. It's negative because it's going down, and that is mission critical. You have to make sure that you have the directions correct with these vectors. Otherwise, bad things will happen mathematically. Okay, so now, those are the only two numbers that were given to us, and we got a lot of blank spots here. So we have a number of things that we need to fill in. Okay, well, another clue is it did say that the flower pot fell. So that means our initial speed or initial velocity in section A is 0 meters per second. Nowhere did it say the number 0 meters per second, but it is implied from the word fall as opposed to thrown. Okay, so the other thing, what we're trying to find is this distance here, which I'm just going to call y. Actually, on second thought, h for height. Okay, so that is going to be related to our dA. So I know that the height and this dA are related. And how they're related is as follows. That projectile over here is going to fall down to the equivalent of that height in section A. So the displacement in A is equal to negative h. The negative because it's going down. Okay, so we still have not a lot of information here yet. We need to solve for this h value, and I only have one piece of information. There are 3 unknowns still in section A. Well, there's some more information. Next, the other thing. There's another number that you know. You just don't realize you know it. The acceleration due to gravity. The acceleration due to gravity, or more commonly just referred to as, g, is equal to 9.8 meters per second squared. However, these questions are vectors. So the acceleration due to gravity, which is a number that you will just memorize, is negative 9.8 meters per second squared because it is going down. And since this is happening on the same planet, section B is the same, it's just in the same spot, really. That's also negative 9.8 meters per second squared. All right, so the good news is we have more information, but we still are missing one thing. We either need the VA2 or the time in section A, and we don't have it. So we only have 2 kinematic parameters, known kinematic parameters for section A, but we have 3. We've got 3 known values in section B. So that means we can solve for any one of these 2. Well, awesome, but how does that help us? The next major important concept is what happens at the transition between A and B. I'll give you an analogy. Let's say you are on a road trip, driving from London to Montreal. So you're en route to Montreal and you're approaching the Ontario-Quebec border. And let's say you are driving at a reasonable speed of 100 kilometers per hour because you always obey the traffic laws. So you're about to leave the province of Ontario at 100 kilometers per hour exactly, and you enter the province of Quebec. At what speed? Well, the same speed that you left Ontario, because the end of Ontario is the exact point in space, the same point in space as the beginning of Quebec. Hence, the end of section A is the exact same point as the beginning of section B. Well, what happens at the end of section A? That is your VA2. 2. And that is going to be equal to the speed at the beginning of section B, which is your VB1. And this is the big deal. Now we have a pathway because we have enough information to find VB1, which means we will then know VA2, which means we can do this. So step 1 is we're going to solve for VB1, which means we don't care about VB2. So to find VB1, we have to pick the one formula that does not have VB2 in it. Well, consulting our list, that would be this one. And you may have noticed that this is one of the more common equations that we use. So dB is equal to VB1T, TB actually, AB, TB squared. All right, so that is our term of concern. We need to get VB1 by itself. So the first thing we have to do is we have to isolate algebraically. And using SAMDEB, bringing that second term over to the left-hand side. And then finally, we're going to isolate for VB1 by dividing both sides by TB. All right, so now we can substitute in. I'm also going to turn the equation around. And again, things to pay attention to. Got to make sure that that dB is negative, and that when you bring this term to the other side, that it becomes negative. And also when you substitute in for the acceleration due to gravity, that you make sure that it is a negative number. And that works out to negative 2.53 meters per second. That makes sense because it is falling down, and therefore the velocity should be negative. Therefore, VA2 is equal to negative 2.53 meters per second. And now we can find H because we now have our VA2. And of course, I put the amber check mark because it's sus, but it's what we have. All right, so that eliminates the time for section A. So now we look at the one formula that doesn't have time in it, and the only formula is equation number 5. So VA2 squared is equal to VA1 squared plus 2A dA. Sorry, 2A subscript A dA. All right, since it starts at rest, VA1 goes to 0. So here's the other thing I'm going to do. I'm going to substitute in negative H for the dA. So we get VA2 squared is equal to 2AA times negative H. I need to get the H isolated by itself. So that means I'm going to remove the 2, the AA, and the negative. Don't get fooled. There is no addition or subtraction here. This is all multiplication because this is 2 times H, AA times H, and negative 1 times H. So I'm going to divide both sides by negative 2AH. So we get negative VA2 squared over 2AA is equal to our height. So now I can substitute in negative bracket negative 2.53 all squared divided by 2 times negative 9.8. Don't forget that negative. Don't forget that negative. Now our final answer has to be a positive number, and it's going to be because these brackets means that the stuff that's inside the bracket becomes positive, but this negative sign here is still negative. It's not affected by the square, and it'll be canceled out by the negative on the denominator. So we get 0.3266 meters, and let's take a look at our, I never filled out my givens there. So the lowest number of sig figs would be 3, so the final answer is 0.327 meters, and there, I filled out the givens. And that's it for sample problem number 7. Next, sample problem number 8. Sample problem number 8. This is, again, another section A, section B problem. And the reason why it is because we have a single object. And this particular object, or this car, is experiencing 2 different types of motion. And the way the question is asked, you can actually parse that out, and I'll show you how you can figure that out based on how things are asked. So let's read it. A car traveling at some unknown speed. So this is important. A car traveling at some unknown speed slows to 72 kilometers per hour. The big idea is this is some unknown initial speed, and this is a final speed. over a distance of 50 meters in 2 seconds. So we know that this is how far it traveled, and this is how long it traveled for. So it's asking us in part A to find the acceleration of the car, and in part B, the initial speed of the car. So far, it only looks like there's one section, but this is where things switch up a little bit. It's in part C. How much further will the car travel before it stops? Okay, so now what we've got going on here is this is something that is outside of this little range of 50 meters and 2 seconds that we started off with. This event over here happens after all of this. So now the idea is we have to kind of modify what's going on here. So what I'm going to do here is I'm actually going to identify this as VA1 for section A, and this would be VA2, and this would be the distance in section A, and this would be the time for section A. Now, actually, I'm going to be a little internally consistent here because I've been highlighting in this sort of green color what we're asked to find. Okay, so in part C, we're asked to find how much further will the car travel before it stops, assuming that we have the same acceleration throughout. Okay, so what that means is what links section A and section B together is a common acceleration. So now, here's the situation that we got going on. It says how much further. So really what we're looking for is the distance in section B before it comes to a stop. So that means at the very end, it comes to a stop. That means our final speed in our second section is rest. And of course, that's an important point as well. All right, so I just cleaned up my GRFS setup because that was an old version. Here's the more modern version where it's a bit more organized. So the first thing I'm going to do is I'm going to break up my given sections, my givens, I should say, into section A and section B. So as a reminder, this is accelerated motion. So what we're going to do is we're going to ensure that we consider all the kinematic parameters associated with accelerated motion. I'm also going to color code it. I'm going to make my section A green and my section B blue. So in our section A, we know that we travel 50 meters. We know we reach 72 kilometers per hour at the end of section A and in a time of 2 seconds. All right, so there should be some red flags going up right now. And that issue should be the 72 kilometers per hour. We need to convert that into meters per second. And how we know we need to convert it to meters per second is because the distance is in meters and the time is in seconds. And if you recall, the quick way to convert from kilometers per hour to meters per second is you divide by 3.6. And this conversion, you can just do right in the given section. So that works out to 20 meters per second. Now, the good news is this. We have 1, 2, 3 given pieces of information, which means we can solve for these other two no problem whatsoever. In section B, we have the following pieces of information. We know that the final speed is 0 meters per second. So that's only one piece of information that we got. Now, in order to solve this question, or the rest of it, and in particular in part C, where we're looking for the distance that we travel in that section, we need to have 2 more pieces of kinematic information. And at the moment, we only have 1. Well, there's one thing that we know. And the clue was over here where it said the same acceleration throughout. That means that we know that the acceleration in section B is equal to the acceleration in section A. So when we find the acceleration of section A, we will have that value for section B, which I've drawn as an amber check mark because, again, it is subject to error. So while we're at it, let's document our RTF. So for part A, we're looking for the acceleration in section A. And for part B, we're looking for the VA1. And in part C, we're looking for the distance in section B. So we know right now we have a problem for section B that we only have 2 known kinematic pieces of information. Well, actually, we only know 1 at the moment, but we will know the acceleration. And it did say very explicitly that the acceleration in section A is the same as the acceleration in section B. But that means we need to know one of these two remaining parameters. We either need to know what the time was for section B or what VB1 is. Some of you already know the answer to that. Awesome. But we're going to come back to that in a moment, because what I'm going to do is I'm going to draw the diagram. And hopefully the diagram will help us answer that next question. So let this line represent the whole motion for section A and section B. We also know that the vehicle is slowing down, which means that these lines will get shorter and shorter and shorter. Kind of regret how I did this now. All right, we'll just get rid of this last little bit. There we go. Okay, so now let's say section A starts here when we're going fastest, and the end of section A is somewhere over here. So all of this is section A. Then that means the remainder is our section B. So right here, that's our VB1. And we know that value to be, actually, I apologize, we don't know what that value is. That's one of the things we need to find. But we do know that the time for this section was 2 seconds. It traveled 50 meters. And we know that the speed at the end of the interval is 20 meters per second. In section B, what we know is that the speed at the end of section B is 0 meters per second. But if you recall, and some of you should already be on this, you should be realizing now that the end of section A is the same as the beginning of section B. And that means our VA2 is equal to our VB1. So that means our VB1 is equal to 20 meters per second. And that means we can modify this now. It's no longer unknown. It's 20 meters per second, and it's also a green check mark. And the reason why? Because it's given. It's a known value. So that's great. We have two known pieces of information that are of top quality in terms of its reliability, and one little unknown, which is the acceleration. Okay, so what we're going to do here is I'm going to finish off labeling all the stuff that we also don't know. So we know that VB1 is unknown, the acceleration in section A, unknown, distance in section A, unknown, time for section A, also unknown, and the acceleration in section A is currently unknown. But we do know, all right, let's try that again. Not section A, for heaven's sake. Oh, well, doesn't matter anyway, because OneNote glitched out again. So I'll have to redraw those anyway. But that's section B, of course, there. And I got it to match that look too. Oh, so nice to glitch out. Okay, so now, first things first, acceleration in section A. Okay, so since we're trying to find the acceleration in section A, actually, no, is that? Yeah, that's right. We're trying to find the acceleration in section A first, which means initially we have to look for the equation that doesn't have VA1 in it. And if we consult our oracle over here to the side, this is the only equation that has no V1. Every other equation has V1, because don't forget delta V means V2 minus V1. So it's equation number 3. So dA is equal to VA2T, subscript A, of course, minus 1/2 AATA squared. Once again, we have to consider SAMDEB, which is BEDMAS in reverse. So you have to do the addition and subtraction first. So again, our term of concern is this one. That's the one that has acceleration in it. And this is what informs me of how I'm going to solve this. There are a couple of ways that you could isolate. Many of you instinctually will probably want to bring that over there. And I will not be doing that. Let me explain. It's that negative. I like to try to avoid unnecessary negativity in an equation. So my approach will be to take this term and bring it to this side, and take this term and bring it over here. So that means we get 1/2 AATA squared is equal to VA2 TA minus dA. Okay, that part's done. Now it's multiplication and division. 1/2 is the same as divide by 2. The opposite of divide by 2 is multiply by 2. Now I'm going to do something intentionally wrong. Did you catch my mistake? Think about it. If you're still unsure, the idea is this. When I bring that 2 over, I have to multiply everything by 2. And what I've done right now is I've only multiplied the first term by 2, but I neglected to multiply the second term. That is a very common error. It's because many students will often forget to put in those brackets there. Next, we have to isolate for the acceleration, which means we have to remove the TA squared, which is attached through multiplication, and the opposite of multiplication, of course, is division. So we have 2 bracket VA2 TA minus dA over TA squared. Substituting in, which equals -5 meters per second squared. And that means the acceleration in section B is also equal to -5 meters per second squared. All right, time to find VA1. So to find VA1, this time we should avoid using the acceleration if we can. I mean, the number was good. There was no rounding error or anything like that. It worked out to a perfectly even number, but there is still the possibility that you made a mistake in the calculation somewhere. So it really is just best to avoid it. So we look for the one equation that doesn't have acceleration in it, and that would be equation number 4. So dA is equal to 1/2 VA1 plus VA2 times TA. Now here's the deal. The VA1 is actually inside a bracket. What some of you might get confused about is when you look at this, technically we do have 2 terms inside the bracket, but we are outside of that bracket at the moment. So what this actually really means, at the moment, this is a single term. The 2 terms that you see are actually embedded inside. So kind of like the layers of an onion, you have to peel those layers away. So that means what we have to get rid of first are these factors that are attached to our bracket. And the 1/2 is attached through division because 1/2 is the same as divided by 2. And the TA is attached through multiplication. So to get rid of the 1/2, we multiply by both sides by 2. And to get rid of the TA, we divide by TA. And then that gives us just the VA1 plus the VA2. That has unlocked what was inside the bracket now. And now those hidden terms are now accessible. So what we then do is we start SAMDEB over again, and we want to isolate for our term of concern, which is our VA1, which means that our VA2 over here has to be removed through subtraction. Okay, so now I'm going to turn the equation around and substitute in. So conveniently, those 2's cancel out. So therefore, our VA1 is equal to 30 meters per second. So finally, we can now solve for dB. Again, we have VB1, we have VB2. We now know what acceleration is in section B, although it is subject to error, obviously, because of our calculation. We were not asked to find time, so we can ignore time in section B. Again, that means we have to look for the equation. Let's clean that up. We have to look for the equation that doesn't have time in it, and that would be equation number 5. That's amazing. I've gone through several of these lessons with that particular error, and that is not good. Well, it looks like I have some older videos to edit. Yay! All right, back to our problem. Jeez, like how do you miss that? All right, anyway. All right, so isolating for dB, doing SAMDEB in reverse. This over here is our term of concern. We have to get rid of the VB1 squared. So we got VB2 squared minus VB1 squared is equal to 2AB dB. The 2 and the AB are attached through multiplication. The opposite of multiplication is division. So we've got dB is equal to VB2 squared minus VB1 squared over 2AB. Turning the equation around, substituting in, and therefore dB is 40 meters. Question number 9. 2 students are randomly attacking each other with water balloons. One student is on the roof and the other is on the ground below. The student on the roof throws a water ball straight down with an initial speed of 5.20 meters per second. And the student below throws his up at a rate of 7.10 meters per second. This particular question is an object A, object B type question. And the reason being is that there are 2 individual water balloons. So our first water balloon, which I will call A, has an initial speed of 5 meters per second down. And the student below throws his up at a rate of 7.1 meters per second. If the height of the building is 10 meters, determine where and when the 2 balloons shall meet. So in this particular question, we have to make sure that we do set up our givens as an object A, object B. So object A, object B. And the other clue is they're throwing them up and down, which means they're subject to gravity. So it's accelerated motion. So we have these parameters for object A and these parameters for object B. And for good measure, let's color code these. So we know that object A is being thrown down, or well, actually it's the balloon A, the first balloon, is being thrown down with an initial speed of 5.2 meters per second. So our VA1 is negative 5.20 meters per second, negative because it's going down. Here's the other thing. We know the acceleration because that is gravity, which is negative 9.8 meters per second squared. And while we're at it, that's also the same for object B because it's the same planet. Now, the other bit of information that we know is we know that object B is being thrown up at 7.1 meters per second. So our VB1 is positive 7.10, 3 sig figs, meters per second. And again, that positive means that it's moving up. Now, let's take a look at what we've got here. So far, in both cases, we have two known bits of information. To solve any equation, though, if you recall, we need to have at least 3 known kinematic parameters. The problem is we only know 2. A couple of other things you have to take into consideration. The only way you can solve this problem is you have to assume that they both launch the projectiles at the same time. Otherwise, there could be many solutions to this problem if their timing is a bit different. So if one does it sooner or after the other, where the balloons will collide will be a different position and a different time. So the first assumption, which is a very good assumption, is that both times are the same. The other piece of information we were given right here, it's the height of the building. What that implies is that the balloons were that far apart initially. This means that our separation distance, or dSep, is equal to 10 meters. The two things that we're trying to find is the position where they meet and the time. Well, the position, I'm going to call y. Now, some of you are saying, don't we usually use x? The reason why I'm using y is because it's in the vertical axis. So I'm just going to use y this time. But if you prefer, you could use x. It doesn't really make a difference, but I thought y made more sense because of the y-axis. So we're looking for this position y, and we're looking for the time. In order to solve, let's make our diagram. Incidentally, this is kind of like an accelerated motion version of Tom and Phil. We had another question where we had kid A and kid B, where kid A was going at a constant speed and constant velocity, I should say, and kid B was accelerating. In this case, both projectiles are accelerating. So let's see how that's going to pan out for us, what it's going to look like. So step 1, let's do the diagram. So the top of the building is position A. That's where our first projectile is. And then at the bottom of the building is where projectile B starts. We know that the building is 10 meters tall. And let's adjust the diagram so it makes a little bit more sense. So they're going to meet somewhere in between. Now, if you notice, I took a gamble. I kind of took a guess that the meeting point is going to be closer to position B than it is to position A. And if you think about that, kind of makes sense. And the reason why is for object A, gravity is working to the advantage on the way down. But for object B, gravity is working against it. Now let's clean that up a little bit. That's prettier. Okay, so I think it's reasonable to assume that it's probably going to be closer to the ground. Again, now that we've got this, I'm going to list my given information on the diagram as I've done before. So for balloon A, the displacement of A is going to be the final position, which is y, minus the initial position, which is 10. The VA1, there we go, is equal to negative 5.10 meters per second. And I suppose technically I should probably put the 0.0 up there. The VA2 is unknown. The acceleration of section A is negative 9.8 meters per second squared. And the time is just t. So for balloon B, the displacement is going to be y minus 0. The VB1 is positive 7.10 meters per second. VB2 is unknown. The acceleration for section B is negative 9.8 meters per second squared, and TB is equal to T. Now, what we have done is we've gone from a total of 10 unknowns initially down to basically technically 4 unknowns. And those 4 unknowns are Y, T, VA2, and VB2. If you recall, we only need to be working with 4 out of the 5 kinematic parameters. So we can actually disregard VA2 and VB2. And the reason why we're disregarding that is because we know nothing of those parameters. But we do know something about the Y and the T. They're shared with both. So now, based on this informs us of what formula we're going to use. And from our list, it is the one formula that doesn't have time in it. Sorry, not time. It's the one formula that doesn't have V2 in it. And that formula would be our equation number 2. So let's start with our equation A. dA is equal to VA1T plus 1/2 AATA squared. Substituting in y minus 10 equals negative 5.1T plus 1/2 times negative 9.8 T squared. Isolating for y is equal to negative 5.1T minus 4.9 T squared plus 10. And that negative 4.9 T squared comes from simplifying this. So we'll call that our equation 1. So our equation for B is in the same form. So y equals positive 7.1T plus 1/2 times negative 9.8 T squared. Cleaning that up a little, we get y is equal to 7.1T minus 4.9 T squared. Now we're going to set the equations equal to each other. So you can either do 1 equals 2 or 2 equals 1. Guess which one I'm going to do. And remember, I always like it so that the variable that I'm trying to solve for is, first of all, on the left-hand side and will be a positive number. If you look at equation 1, that number is negative. So maybe I don't want that one on the left-hand side. This one is positive. So maybe I want that one on the left-hand side. And I do, in fact, want that one on the left-hand side. So I'm going to do equation 2 equals equation 1. So equation 2 equals equation 1. That gives me 7.1T minus 4.9 T squared is equal to negative 5.1T minus 4.9 T squared plus 10. Zooming in, a little bit of good news here. Notice this. We have, put that decimal place back. We have a negative 4.9 T squared on the left side and a negative 4.9 T squared on the right, and they eliminate. And that is a nice relief because that reduces the quadratic property of this question. And then all of a sudden, it becomes a linear question. So now, collecting like terms, oh, and I just caught a mistake. Not 5.1, but 5.20. All right, well, that's a drag, but we'll fix that. All right, and one more spot, I guess 2 more spots, 5.2, 5.2, and 5.2, which makes that now 12.3. So isolating for t, that's going to be 10 over 12.3. As a fraction, that's 100 over 123. As a decimal, that's 0.8130. And that's actually all repeated. And that's good enough for us. Now, of course, we write it as 3 sig figs. So that's 0.813 seconds. And now that we have the time, we can find position y using either equation 1 or equation 2. I'm going to choose equation 2 because it's a little easier to work with. So using equation 2 and what we got for time, and even color code it. So y is equal to 7.1t minus 4.9t squared. The better value to use is the 100 over 123, but you can also use the decimal version of the number, but the fraction is better because it introduces less error. But you have to be really careful when you plug it into your calculator. So physics is as much science and mathematics as it is calculator gymnastics. So we get 2.5335448 yada yada yada. And that's meters, but we have to round it off to 3 sig figs because that's what the original numbers were in. So therefore, that position Y is 2.53 meters above the ground. And that's it. And finally, question number 10. This question I like to affectionately refer to as the Dream Crusher. Now, that's obviously an intimidating title, but essentially it has to do with the complexity of the algebra in this one. And this one is really more of a grade 12 level question. So this isn't something that I would really put on a grade 11 test, but I feel that if you can handle this particular question and the algebra involved, I think we're going to be good. So let's take a quick look at what's going on with this question in particular and why it has earned the esteemed distinction of being called the Dream Crusher. A student is running a race that is a distance of 5,000 meters. The student wishes to complete the race in a total of 13 minutes. The student completes the first 4,200 meters in 11 minutes. If he or she is able to accelerate at a rate of 0.2 meters per second squared, determine how long he or she must accelerate for them to complete the race in the desired time. Assume that the motion, and this is another key point, is constant in every other part of the race. So the idea here is that there is only accelerated motion in one section. What makes this question so uniquely challenging is that it is multiple sections. It's not just two sections, but in fact, there are three sections. So in order to solve this, we're going to have to start off with a diagram because it really is a lot easier to imagine this in how we approach it. The solution is if you can see what's going on. So I'm going to make an actually fairly substantial diagram to do this as opposed to doing the traditional GRFS business. I have found that the best way to represent this is to create, and it's kind of an unusual style, but I think when you see it, it'll make sense why I choose this particular perspective of speed versus the position. The first thing that we know is that the entire race is 5,000 meters long, and the total time for the race was 13 minutes. We're going to pause there for a second. 13 minutes is not really the ideal amount of time, the unit of time that we want to work with. So since the distances are in meters, we really need to consider the time ultimately in seconds. But for now, we'll leave it at 13 minutes. And then later on, when we break it up into the three sections, we'll then convert those times into seconds. The first part of the race was 4,200 meters long. So that's really the majority of it. I'm not going to draw it to scale. And the reason why, because we have to do a lot of writing for the accelerated motion section. So I'm going to start off like this. The green section, this will be our first section. And let's say that'll be the 4,200 meter section. Obviously, normally we would extend this further, but it's good enough for now. And we'll make that a little bit wider there. Okay, so let's call this our section A. Now there's actually a couple of ways that we could look at it. There are two ways that our runner could have finished the race. They could have waited to the end to do the acceleration, or do the acceleration first and then run the remainder of the race at a constant speed. The easier way to do this is to have the acceleration at the end. So therefore, that's not how we're going to do it. Obviously, we're going to do it the harder way. Why? Because we like to flex with the algebra. So that's what we're going to do. And we're going to have it so that the next section, our section B, is the section where we experience acceleration. And now you can kind of get an idea of why I'm drawing it this way. So the speed or velocity, I guess, depending on our perspective, is going to increase during that section. So what I have in blue, that is our section B. And then finally, at the end, the remainder of the race, that is our section C. Okay, good. So far, so good. Okay, so let's see if we can do a little bit more of an analysis of what's going on. Now, to help us out even further, I'm going to further separate the sections with these vertical lines so we can see them as distinct as they are. So the next step, we're going to start filling in our given information for each section. Note, A is constant motion, and we have some information that we know about section A. First of all, we know that the distance traveled in section A was 4,200 meters and to 4 sig figs. There we go. Now the time is 11 minutes. So the time for section A equals 11 minutes, which we need to convert to seconds. And of course, there are 60 minutes in a second, which works out to 660.0 seconds. And the speed for section A is unknown. But if you look, we have both the distance and the time for section A. So finding the speed for section A, not a problem. Now let's focus on section B. On section B, we know the rate of acceleration. But since it's accelerated motion, we have the following kinematic parameters that we need to deal with. We have dA, VA1, VA2, acceleration in section A, and the time for section A. Except that should be all section B. Let's fix that. So in section B, we know the acceleration is 0.2 meters per second squared. And so far, that's kind of all we know. Well, we actually know a few more things, but in terms of the information, here, and I'm going to move the C over here. While we're at it, we might as well talk about section C. And in section C, since it is also constant motion, we have the three kinematic parameters: distance in C, the speed in C, and the time in C. So there are a lot of blank spots that we need to fill. And that's what makes this question pretty intense. So if you see here, and just to give you some idea, VA is unknown, so that's 1 unknown. DB is unknown, so that's 2. VB1, unknown, 3. So now VB2, that makes 4. TB, 5. DC, 6. VC, 7. TC, 8. We have 8 unknowns. That means we actually have to come up with 8 different equations. Okay, now some of these equations are not actually equations, but they're actually relationships. But technically they're equations because they have an equal sign in them. So we actually have to come up with 8 different equations to solve this with the kinematic formulas for constant motion. We know the basic formula for that, but we're going to have a lot of work to relate these things to. Now, there's some other information that we have to take into consideration. We haven't yet, but I'll get to that in a moment. A couple of things I want to talk about is the relationship at the borders between sections A and B and C. And concept number 1, big concept, is that the speed at A must be equal to the speed at the beginning of B. So VA equals VB1. So there's one of the 8 equation relationships. So by doing that, when we solve for VA, we will know what VB1 is. We also know that VB2 must equal VC. So that's another relationship. So there's the second one. Only 6 more to go. All right, so now the next big idea. Don't forget, we also know that the total race was 5,000 meters and the total race was run in 13 minutes. Of that amount, the first 4,200 were done in 11 minutes. So what that means is we actually have enough information to know how much time was left for both B and C combined. So we'll take a look at this. We know that the remainder of the race has to be 800 meters. It has to be done in 2 minutes. So what that means is part of this 800 meters is done in section B, and part of this 2 minutes is done in section B. Now, this is the time that we have to talk about seconds. So that 2 minutes, that's 120 seconds. So here's the thing. Let's talk about this 800 meters. So I don't know how much belongs to section B and how much belongs to section C. So what I'm going to say is the following. Let the distance in section B equal to x. I don't know what x is. That's something that we're going to have to find out. But I do know that means is that the distance in section C is going to be 800 minus x. So by doing this, I've actually got rid of dB and dC and have expressed it in terms of the same variable. So I've taken two unknowns, dB and dC, and expressed it as a single unknown, x. So that's another relationship that we just added of the total of 8 that we had to come up with. We can also do the same thing for time. So the time for section B is going to be part of the 2 minutes, and the remaining part is going to be for section C. So let's say the time in B is equal to T, and let's say the time in C is going to be 120 minus T. Okay, so we're getting rid of a bunch of these question marks here. So the next thing we're going to do is we're actually going to start solving some things mathematically. Here is your approach when you're doing these questions. Section B is accelerated motion, which means that there are like 5 different unique formulas that we could be working with. But with section A and section C, there's only one, which is the constant motion formula. And for section A, since we know all the numbers, we're going to start off with that very first equation, and we're going to solve for VA first, which means we will also know what VB1 is. So to find VA, we know that VA is equal to dA over TA. And the dA was 4,200. The TA was 660 seconds. We're going to drop all the extra sig figs for the interim calculations. And this works out to 70 over 11 seconds. Now, you might be saying to yourself, well, why don't we just put that as a decimal? Well, no, we're not going to do that. And the reason why is because if we leave it in the fraction form, there's some good cancellation that happens. All right, so now we know the time in section A. So now we know what our VB1 is going to be. So our VB1 is equal to 70 over 11 seconds. So what I'm going to do here is on the side here, I'm going to put my updated values. So we now know that our VB1 is equal to 70 over 11 seconds. All right, so now if we look here, we've got 1, 2, 3 unknowns. That means we're down to only needing 3 more equations. Okay, so next, we're going to focus on section C because we know the formula for that one because it's constant motion. So let's go down over here. So we're going to find VC. Now, it's funny that I say we're finding VC. We're actually finding an expression for VC. So that's equal to DC over TC. But DC is equal to 800 minus X. And the TC is equal to 120 minus T. Yep, not pleasant. But now we know VB2 is equal to this expression of 800 minus X over 120 minus T. So updating our VB, 800 minus X over 120 minus T. So now we are down to one unknown, that's the X, and our second unknown, the time. So we have 2 unknown variables now. That means we need 2 more equations. So what we've done here is we've focused entirely on trying to get something going on in the section B. And we have reduced it down to 2 unknown variables, X and T. Since we are now in the constant motion section, we now have to focus on the constant motion formulas. Not constant motion, my goodness. The accelerated motion, let's try that again. Since we're in the accelerated motion section, I apologize, we now have to focus on the accelerated motion equations. So we're going to grab a copy of those, and then we're going to see which ones we're going to work with. Okay, so now here's the thing. All of these will work. But what we want to do is we want to make the least ugliest equations we can find. The big problem at the moment is the VB2. That has a complex expression in it. So what that means is that when we do introduce an equation, since we have to have 2 more equations that come from this list, that means all 5 kinematic parameters are going to be involved. What you want to do is spare yourself the emotional pain of picking the wrong equation. Let me give you an idea of a wrong equation. you already see that VB2 is a complex expression. Do you really want to have that squared? So maybe we'll avoid that one if we can. This one is inside a bracket, so that would make the algebra harder. So again, when it comes time to using VB2, we will try to pick the easier of the equations to work with. But for now, our first equation, we can actually avoid working with VB2. So we can work with this equation here because it doesn't have the VB2 in it and it's less complex. So using that equation number 5 here, and let's try that again. We're not using equation 5, we're using equation 2. We want to avoid using equation 5. So using d is equal to v1t plus 1/2 at squared. So by doing that, we got db is equal to vb1 tb plus 1/2 ab tb squared. Substituting in, x equals 70 over 11, yuck, times t plus 1/2 times 0.2 t squared. Cleaning that up, we get x is equal to 70 over 11t plus 0.1 t squared. So since we've got these numbers over here, let's call this equation A. So next, since we can't use this equation anymore, we have to use an equation that involves VB2. So we're going to pick one that is the least terrible. I think that's terrible because you got to multiply by t. That's terrible because you're inside a bracket and just gross. Like, come on, squared? No. This one, yeah, this one is probably the best one because it's just V2. Here, put my check mark over there. It's just V2 isolated on the left-hand side. And again, as I mentioned before, it's not as horrible as the other ones. So that's what we're going to do. So V2 is equal to V1 plus AT. So we've got VB2 equals VB1 plus AB TB. Our VB2 is 800 minus X over 120 minus T. And that's equal to 70 over 11 plus 0.2 times T. And again, I'm going to apologize in advance to what I'm about to do to you. This X here has to be combined with this X over here. So you kind of have to accept the fact that we have a lot more algebra to do before we're ready to set these equations equal to each other. The biggest issue is, do you want to really substitute this whole expression into the numerator on the left-hand side here and then have to get rid of this denominator? You're not going to want to do that. What you're going to want to do is you're going to want to isolate for this X. And no matter how you slice it, it's a little bit ugly to get there. But if you're patient and you just follow the rules of mathematics along, it is very doable. So the first thing we're going to do is we're going to get rid of the 120 minus t that it's on the denominator. And to do that, since it's divided, so the term on the numerator is divided by a term on the denominator, we are going to remove this term on the denominator via multiplication. Because since it's in the denominator, that's division. The opposite of division is multiplication. So this becomes 800 minus x bracket equals 120 minus t bracket 70 over 11 plus 0.2 times t. Yes. Next, binomial expansion. And that's the whole FOIL thing. So first, outer, inner, then last. And if you folks don't remember FOIL, if you didn't do FOIL before, the other way to do it is use distributive property across these two. So using distributive property is the exact same way. And depending on who you had in grade 10, they would have either shown you the FOIL method or distributive property or both. But I will actually use the distributive property because I think that's the one that most people commonly know. If you know the FOIL method, by all means, do that. Now, I've distributed that, but the problem is it's backwards. Well, not really backwards, but it's better to have the single factor in front as opposed to the double term. Same with this one. So what I'm going to do is I'm going to rewrite it, but in this order. Because as far as distribution goes, that is a little bit more familiar for most. So next, let's distribute in both those terms. So we've now completed the distribution. So we're going to hold up on something here because, usually you collect like terms, but we're going to not do that in this case because in this equation up here, we have this. So what we're going to do is we're going to isolate for x. That means we're going to bring this x to the right-hand side to make it positive, and that means we have to bring all of this to the left-hand side, which is going to make everything its opposite sign. So now we have 800 minus 8400 over 11 plus 70 over 11t minus 24t plus 0.2, and that should be t squared equals x. I am going to collect one like term, well, two like terms. I'm going to focus on that there, on the constant. So I'm going to get this with a common denominator, which means to turn 800 into a denominator of 11, I have to multiply it by 11 over 11. So that makes it 8800 over 11 minus 8400 over 11 plus 70 over 11t minus 24t plus 0.2 t squared equals x. Okay, we're getting close. So I'm going to do two more things. I'm going to turn the equation around so that the x is on the left-hand side. So basically just do a 180, and I'm going to combine these two terms. So we get x equals 0.2 t squared plus 70 over 11t minus 24t plus 0.2 t squared plus 400 over 11. Okay, and we're going to call that our equation B. Oh boy. So now we've got our equation A up there. We have our equation B down here. Time to combine the two. And I'm going to set it so that B equals A. So writing this all out, and apparently I have a bit of a stutter up here. It's like, yeah, I thought there was two extra terms there. We'll give that a little something there. Look a little bit more sensible. Okay, so let's just double check. Let's make sure I didn't add some more random things to make things even more complex. Yep, so it looks like we're good. All right, so now that's equal to equation A, which is 70 over 11t plus 0.1 t squared. Great. Now we can take advantage of this because that 70 over 11 mercifully gets canceled out. So now the next thing we're going to do is I'm going to bring all the terms to the left-hand side and collect all like terms and have you enjoy the fact that now we have to use the quadratic formula with a fraction. So our A value is equal to 0.1, our B value, negative 24, and our C value, 400 over 11. So the quadratic formula is t, not x in this case, because the variable is t, not x. So that's equal to negative b plus or minus b squared minus 4ac over 2ac. Oh, 2a for heaven's sake, ac. Good gravy. Substituting in, which is quite the expression. And now we have to solve for our t1 and our t2, because we will get 2 times out of this. And now the issue. We have 2 positive times. They're both positive. So it's not immediately clear which of the 2 numbers we're going to take. But obviously, one of them has to be correct and the other one has to be wrong. So how do we figure it out? Well, there's a clue. And that has to do with how much time was left at the end of the race. Let's go back to the diagram. So when you go back to the diagram, the end of the race, there were only 2 minutes left, which means that there was a total of 120 seconds only. There's only 120 seconds left. So that means the maximum in one section would be 120 seconds. That's the absolute upper limit, I meant. So now, since 120 seconds is the absolute limit, that means we can't use this time because that exceeds 120 seconds. So therefore, the amount of time they must have accelerated for was 1.5248 seconds, or to 4 sig figs, 1.525 seconds. And congratulations on completing your first Dream Crusher.